The James Webb Space Telescope was not designed to surprise astronomers. It was designed to test ideas that already existed, to extend known models deeper into space and further back in time. Its purpose was verification at the limits of observation, not the discovery of phenomena that fall outside expectation. The assumption was that the universe would become clearer, not stranger, as resolution improved. That assumption has proven unreliable. In one of JWST's deep-field observations, astronomers encountered an object that immediately resisted classification. It was not faint because of distance alone. It was not bright because of known energy sources. Its structure, luminosity, and inferred physical properties did not align with the behavior of stars, galaxies, or compact remnants as they are currently understood. The problem was not a lack of data. The problem was that the data were internally consistent and still incompatible with prediction. This object was not identified because scientists were looking for something unusual. It emerged during routine analysis of deep space observations intended to study early cosmic structure. At first glance, it appeared as a minor irregularity, a signal that seemed out of place but not necessarily significant. Similar irregularities often turn out to be processing artifacts, background contamination, or statistical fluctuations. The standard response is verification, not alarm. Verification did not resolve the issue. The object persisted across independent observations, across different filters, and across separate analysis pipelines. Instrumental explanations were eliminated early. Calibration errors were ruled out. The signal did not weaken with scrutiny. It became sharper. As more parameters were measured, the conflict with established models increased rather than diminished. What made the object difficult to interpret was not a single anomaly, but the way multiple properties contradicted one another. Its apparent size did not match its brightness. Its energy output did not match its inferred mass. Its location in cosmic time did not match the stage of structure formation required to produce it. Each discrepancy on its own might have been accommodated. Taken together, they formed a system that did not belong anywhere in existing frameworks. Astronomy is accustomed to rare objects. Quasars were once considered inexplicable. Neutron stars were theoretical before they were observed. Even black holes were treated cautiously for decades. In each case, the discovery fit within physics once the correct interpretation was found. The situation here is different. This object does not simply stretch a model. It forces multiple models into tension simultaneously. The difficulty is not that the object violates a single rule. It violates several assumptions that are foundational to how deep space objects are understood. These assumptions are not arbitrary. They are derived from decades of observation, simulation, and cross-confirmation. They describe how matter collapses, how energy is generated, how structures grow, and how time constrains those processes. The JWST object sits at the intersection of these assumptions and undermines their coherence. Initial attempts to classify the object followed standard procedure. Researchers asked whether it could be an early galaxy. The spectral data resisted that interpretation. They asked whether it could be a compact object such as a black hole system. Key signatures were missing. They examined whether it might be a transient phenomenon. Its stability over observation time ruled that out. Each explanation required introducing additional assumptions that created further inconsistencies elsewhere. This escalation was quiet. There was no public announcement declaring a crisis. In astrophysics, anomalies are treated conservatively. Language is restrained, claims are narrowed. Yet behind that restraint, the implications were clear. If the object was real, and the data suggested it was, then either something fundamental about early cosmic physics was incomplete, or an entirely new category of object had been observed. JWST's role in this is not incidental. Previous telescopes were not blind to the region of space where the object exists, but they lacked the sensitivity to resolve its properties. In optical wavelengths, the object blends into the background. In earlier infrared surveys, it appears unresolved or ambiguous. JWST's infrared instruments, designed to detect faint thermal and redshifted signals, provided clarity where none existed before. This clarity did not simplify interpretation. It removed plausible excuses. The telescope did not reveal chaos. It revealed order that does not belong to known systems. This distinction matters. The object is not poorly behaved. It is stable, persistent, and measurable. Its behavior is coherent. The problem is that the coherence is incompatible with what physics predicts should be possible under the conditions inferred. This makes the discovery more troubling than a noisy or transient signal. It suggests that the universe can assemble and maintain structures under constraints that have not been accounted for. The phrase bizarre object is not used here to imply mystery for its own sake. In scientific terms, the object is bizarre because it occupies a region of parameter space that was not expected to be populated. Models of cosmic evolution predict where matter should cluster, when it should do so, and what forms it should take. This object exists outside those predicted regions without violating observational consistency. That combination is rare. If the object were closer, its properties might be dismissed as a local oddity. If it were farther, uncertainties might obscure interpretation. Instead, it exists at a distance and redshift where measurement precision is sufficient to make the contradictions unavoidable. Its position in the universe makes it relevant to questions about early structure formation, not peripheral to them. As the analysis continued, the scope of the problem expanded. The object was not merely difficult to explain on its own. Its existence had implications for other observations. If such an object can exist, then assumptions used to interpret deep field surveys may need revision. The number of similar objects could be underestimated. Entire populations might be misclassified or missed altogether. This possibility introduces a broader concern. Cosmology relies on statistical inference. Large-scale conclusions are drawn from samples that are assumed to be representative. If certain classes of objects are systematically excluded because they do not match expectations, then conclusions about the early universe may be incomplete or biased. JWST was built, in part, to reduce such biases. Its sensitivity was intended to provide a clearer census of early cosmic structures. Instead, it has exposed gaps between observation and interpretation. The object at the center of this script is one such gap, sharply defined and resistant to resolution. What follows is not an argument that existing physics is wrong. It is an examination of where existing physics reaches its limits. The goal is not to speculate beyond evidence, but to follow the evidence precisely to the point where explanations fail. This object forces that exercise. The sections that follow will describe what JWST observed, how those observations were confirmed, and why each plausible explanation encounters obstacles. The discussion will remain grounded in data and established theory, even as it confronts their shortcomings. No single discovery overturns a field. But some discoveries reveal that the field has boundaries it did not know existed. This object is one of those cases. It does not announce a new theory. It does not provide answers. It presents a contradiction that cannot be ignored. The significance lies not in what it is claimed to be, but in what it demonstrably is not. JWST did not set out to find the most bizarre object in deep space. It set out to look carefully. This object is the result of that careful looking, and its existence now demands careful explanation. Chapter 1. What JWST actually saw. The initial detection of the object did not occur during an experiment designed to search for anomalies. It emerged during routine analysis of deep field observations intended to study early cosmic structure. These observations were part of a broader effort to measure the distribution of galaxies at high redshift, trace star formation rates in the early universe, and refine models of large-scale structure formation. The object appeared as a compact source embedded within a field of otherwise well-understood signals. At first, there was no immediate indication that the detection was extraordinary. Deep field images routinely contain thousands of faint sources, many of which require careful filtering before they can be interpreted. Astronomers expect to encounter noise, background fluctuations, and blended sources at the sensitivity limits of any telescope. The object initially registered as a weak but consistent signal across multiple infrared bands. What drew attention was not its brightness alone, but its consistency. The source appeared in independent exposures taken at different times and through different filters. Its position remained fixed relative to background reference points. This ruled out transient phenomena, such as cosmic rays, detector glitches, or moving foreground objects. The signal behaved like a genuine astrophysical source. JWST's infrared instruments provided the first detailed look. The object emitted strongly at wavelengths associated with redshifted light from the early universe. Its spectral energy distribution did not resemble that of typical stars in the Milky Way, nor did it match the expected profiles of known background galaxies at comparable distances. The emission pattern was coherent but unusual, with intensities that did not scale as expected across wavelengths. Astronomers began by applying standard classification pipelines. These pipelines are designed to sort detected sources into broad categories based on brightness, color, morphology, and spectral features. The object resisted this process. It failed to meet the criteria for a normal star. It also failed to align with templates for known galaxy populations, including early star-forming galaxies commonly observed at high redshift. One of the first anomalies involved its apparent compactness. In JWST images, the object appeared spatially concentrated, lacking the extended structure typical of galaxies at similar distances. Early galaxies often appear irregular or clumpy due to active star formation and mergers. This object showed no such features. Its light was confined to a small region, closer in appearance to a point source than to a diffuse system. At the same time, its brightness was inconsistent with that interpretation. Objects of comparable compactness are usually either foreground stars or compact remnants, such as active galactic nuclei. Foreground stars can be ruled out by their color signatures and parallax behavior, neither of which matched the data. Active nuclei typically show characteristic emission lines and variability patterns, which were absent or inconsistent in this case. Spectral analysis added further complications. The object's spectrum lacked several features that astronomers rely on to identify stellar populations, such as clear indicators of ongoing star formation. At the same time, it did not exhibit the strong signatures expected from accretion onto a central compact object. The spectrum suggested a source of energy, but not one that fit known mechanisms cleanly. Redshift estimation placed the object at a significant cosmological distance. This positioning implied that the light observed had been traveling for a large fraction of the universe's age. Objects at this distance are expected to be either early galaxies undergoing rapid formation or massive energetic systems driven by extreme processes. The observed properties did not align with either expectation. The inferred luminosity presented a further contradiction. Based on its distance, the object emitted more energy than its size and apparent structure should allow. Scaling relations used across astrophysics link size, mass, and luminosity in predictable ways. This object deviated from those relations. If its luminosity estimate was correct, then its physical mass or energy generation mechanism would need to be unusual. Astronomers tested whether dust extinction or geometric effects could explain the discrepancy. Dust can obscure and redden light, altering apparent brightness and structure. However, modeling showed that dust alone could not reconcile the observed spectrum with standard templates. The object's emission remained anomalous even after accounting for plausible dust scenarios. Repeated checks focused on calibration. JWST's instruments undergo extensive calibration procedures to ensure accuracy. Data from different detectors were compared. Background subtraction methods were varied. The object remained. Each adjustment confirmed that the signal was not an artifact of processing choices. As confidence in the detection grew, the focus shifted from verification to characterization. Researchers attempted to constrain physical parameters such as size, temperature, and energy output using available data. Each estimate introduced uncertainty, but all plausible values remained in tension with existing models. No combination of parameters resolved the contradictions cleanly. The object also lacked obvious environmental context. It did not appear embedded in a dense cluster of galaxies. There were no nearby structures that could easily account for its properties through interaction or merger. Its apparent isolation removed another potential explanatory pathway. This absence of context matters because environment plays a key role in shaping astrophysical systems. Interactions can compress gas, trigger star formation, or fuel energetic processes. Without evidence of such interactions, the object's properties must arise from internal conditions or from formation processes that differ from those commonly observed. At this stage, the object was not yet described as unprecedented. Astronomers are trained to assume that unusual signals will eventually find explanation within known physics. The working assumption remained that additional data or refined analysis would resolve the inconsistencies. However, as more measurements were layered onto the initial detection, the space of plausible explanations narrowed rather than expanded. Each attempt to classify the object within an existing category required additional assumptions that created new problems elsewhere. The object did not merely stretch known categories, it occupied a position between them. This resistance to classification marked a turning point. The question shifted from, "What is it?" to, "Why does it not behave like anything we expect to see?" This is a subtle but important change. Astronomy often encounters rare or extreme objects. It encounters far fewer objects that undermine multiple independent expectations simultaneously. JWST's role in this shift cannot be overstated. The telescope's sensitivity allowed astronomers to move beyond detection and into detailed measurement. Earlier instruments might have registered the object as a faint source and left it unresolved. JWST provided enough information to reveal inconsistency rather than hide it. By the end of initial analysis, several conclusions were clear. The object was real, it was distant, it was stable over the observation period, and its observable properties did not align with any standard class of astrophysical object. These conclusions did not explain the object, but they defined the problem space precisely. What JWST actually saw was not chaos or noise. It saw a coherent, persistent source whose existence raised questions about how matter behaves under early cosmic conditions. The challenge was not that the data were ambiguous. It was that the data were too clear to ignore. With the observational facts established, attention turned to why earlier telescopes had not revealed the same contradiction. Understanding that limitation is essential to understanding why this object has only now come into focus. Chapter 2. Why earlier telescopes did not see the problem. The absence of this object from earlier astronomical catalogues does not indicate that it was invisible, but that it was unresolved in ways that mattered. Previous telescopes detected light from deep space, but they did not detect contradiction. What changed with JWST was not merely sensitivity, but the ability to separate overlapping explanations and test them against one another. Earlier space telescopes, most notably Hubble, were optimized for optical and near-ultraviolet wavelengths. These wavelengths are effective for studying relatively mature stars and galaxies, but they become increasingly limited when observing objects whose light has been stretched by cosmic expansion. At high redshift, radiation emitted in ultraviolet or visible bands arrives at Earth shifted into the infrared. Hubble could detect some of this light, but only weakly and without the resolution required to analyze fine structure or detailed spectra. Ground-based observatories face additional constraints. Earth's atmosphere absorbs and distorts large portions of the infrared spectrum. Adaptive optics and specialized instruments mitigate some of these effects, but they cannot replicate the stability or sensitivity of a space-based platform operating far from Earth. As a result, Faint and compact objects at extreme distances often appear blended with background noise or are misclassified as ordinary sources. In earlier surveys, an object like this would likely have been catalogued as a faint point source with insufficient data to warrant further scrutiny. Its compact appearance would have encouraged classification as a distant galaxy nucleus or a foreground star, depending on color and brightness. Without reliable spectral information, these classifications would not have been challenged. JWST altered this situation by operating across a broad infrared range with unprecedented sensitivity. Its instruments can detect subtle differences in spectral energy distributions that were previously indistinguishable. Where earlier telescopes saw a single data point, JWST resolves a pattern. Where previous observations allowed ambiguity, JWST removes it. This matters because many astrophysical classifications rely on patterns rather than absolute values. A galaxy is identified not by brightness alone, but by how brightness changes with wavelength, how light is distributed spatially, and how spectral features align with known physical processes. Earlier telescopes lacked the ability to assemble these patterns for extremely faint sources. Another limitation of earlier observations was survey depth versus coverage. Deep surveys focus on small regions of sky to maximize sensitivity, while wide surveys sacrifice depth for breadth. Objects like this one fall between these approaches. They are too faint to stand out in wide surveys and too rare to be guaranteed inclusion in narrow, deep fields. JWST's observing programs combine depth and resolution in a way that increases the likelihood of detecting such borderline cases. Temporal coverage also plays a role. Many earlier observations were limited in duration or repeated infrequently. This restricts the ability to confirm persistence and rule out transient effects. JWST's observing strategy allows for repeated measurements under consistent conditions, strengthening confidence in faint detections. It is also important to consider theoretical expectation as a filtering mechanism. Astronomers interpret data within the framework of what they expect to find. When an object's properties fall within known categories, it is catalogued and set aside. When properties are ambiguous, they are often assigned to the nearest plausible class. Without compelling reason to do otherwise, anomalies can remain unnoticed. This is not a failure of methodology, but a consequence of scale. Earlier telescopes operated closer to the limits of detection, where uncertainties dominate interpretation. In that regime, unusual objects are absorbed into noise or averaged into existing populations. JWST moves that boundary. It brings certain objects out of ambiguity and into contradiction. The difference is evident in how the object behaves across wavelengths. In JWST data, its emission does not scale smoothly with wavelength as expected for known sources. Earlier telescopes lacked the sensitivity to detect these deviations. They could measure presence, but not behavior. JWST also benefits from improved calibration and stability. Its detectors are designed to minimize systematic errors that become significant at low signal levels. This reduces the likelihood that unusual spectral shapes are artifacts of instrumentation rather than real physical features. Another factor is the refinement of data analysis techniques. Modern pipelines incorporate more sophisticated statistical models and simulations. These tools allow astronomers to test whether observed properties are consistent with known populations or represent outliers. In earlier eras, such analyses were computationally impractical for large datasets. Taken together, these differences explain why the object did not trigger concern before. It was not absent. It was unresolvable in the ways that matter for interpretation. JWST did not reveal a hidden object, so much as it revealed the inadequacy of earlier explanations. This distinction is crucial. The discovery does not suggest that the universe suddenly produced something new. It suggests that the universe has always contained structures that exceed the resolution of prior models. JWST's contribution is not to invent anomalies, but to expose them. By making this object visible in sufficient detail, JWST transformed it from a statistical possibility into a physical problem. The question is no longer whether the object exists, but why existing frameworks did not anticipate it. With the observational limitations of earlier telescopes understood, the focus can now shift to where this object exists in the universe and why its location amplifies the difficulty of explanation. Chapter 3. The object's location in cosmic time. Once the object's detection was established and instrumental explanations were excluded, the next critical parameter to constrain was its location in the universe. In astrophysics, location is not simply a matter of distance, it is a proxy for time. Because light travels at a finite speed, observing distant objects means observing the universe at earlier stages of its evolution. Where an object appears along this timeline determines which physical processes could plausibly have produced it. Redshift measurements placed the object deep in cosmic history. Its light had been stretched significantly by the expansion of the universe, indicating that it originated when the universe was far younger than it is today. This immediately narrowed the range of viable explanations. Many astrophysical processes require long periods to operate. Others depend on environmental conditions that did not exist in the early universe. The object's redshift excluded these pathways before detailed modeling even began. At such early epochs, the universe was denser, hotter, and less chemically evolved. Heavy elements had not yet accumulated in large quantities. Star formation was only beginning to organize into recognizable galactic systems. Structures observed at this time are typically irregular, actively forming stars, and embedded within dynamic environments shaped by mergers and gas inflows. The object observed by JWST did not conform to this pattern. Its apparent maturity was inconsistent with its age. Objects at similar redshifts usually show clear signs of rapid assembly. Their structures are chaotic, their spectra dominated by young stellar populations, and their energy output driven by intense star formation or accretion. In contrast, the JWST object appeared compact, stable, and energetically coherent. This stability is difficult to reconcile with the turbulent conditions expected at that point in cosmic history. The timing problem becomes more pronounced when formation timescales are considered. To reach its inferred properties, the object would have needed to assemble mass, organize structure, and generate energy within a relatively short window after the Big Bang. Standard models allow for rapid growth under certain conditions, but those conditions leave distinct observational signatures. Many of those signatures were absent. This creates a tension between when the object exists and what it appears to be. If it formed early, it should exhibit the characteristics of early formation. If it formed later, its redshift should be lower. The data indicate neither scenario cleanly. The object occupies a region of parameter space where formation pathways are constrained by time and environment simultaneously. The location also complicates environmental explanations. At this redshift, large-scale structures such as galaxy clusters were not yet fully established. Interactions that might produce unusual objects today were less common or operated differently in the early universe. The object's isolation reduces the likelihood that its properties result from recent mergers or external triggers. Another implication of its location is its relevance to cosmological models. Objects observed at this distance contribute to the statistical picture of early structure formation. If such an object exists, it implies that the distribution of early structures is broader than predicted. It raises the possibility that similar objects may exist, but remain undetected due to observational limits. The redshift also affects how physical properties are inferred. Distance estimates feed directly into calculations of luminosity, size, and energy output. Errors in redshift propagate through all subsequent analysis. For this reason, redshift determination received careful scrutiny. Multiple methods were applied to ensure consistency. The result remained stable. With the object firmly placed in early cosmic time, the scope of the problem sharpened. Its properties were not merely unusual in isolation, they were unusual given when and where it exists. This temporal context transforms the discovery from a classification challenge into a fundamental question about how the early universe behaves. Understanding why this object exists at this point in cosmic history requires confronting assumptions about the pace of structure formation and the range of physical conditions present shortly after the Big Bang. It also forces a re-evaluation of how rare or common such objects might be. With its location in cosmic time established, attention turns to the relationship between its size and inferred mass. This relationship introduces the first quantitative contradiction that resists simple explanation. Chapter 4: A Size-Mass Relationship That Should Not Be Possible. Once the object's distance and epoch were confirmed, astronomers moved to what should have been a routine step, determining how large it is and how much mass it contains. In astrophysics, this relationship is one of the most stable and well-tested frameworks we have. Across cosmic time, from nearby galaxies to the earliest structures after the Big Bang, size and mass tend to evolve together in predictable ways. Deviations happen, but they usually fall within understood limits. What JWST revealed here did not. The first clue came from direct imaging. The object appeared astonishingly compact. Its light was confined to a region far smaller than expected for a system producing such intense emission. Even accounting for resolution limits and projection effects, the structure was tight, dense, and sharply bounded. There was no extended halo of diffuse starlight, no obvious outskirts fading gradually into darkness. Instead, the brightness dropped off quickly, suggesting that most of the emitting material was concentrated in a very small volume. On its own, compactness is not unprecedented. Astronomers have seen compact galaxies before, particularly in the early universe. But compact objects usually come with a trade-off: lower total mass or short-lived instability. This object violated that trade-off almost immediately when its luminosity was analyzed in detail. Luminosity is not mass, but it is tightly connected to it. Producing large amounts of light requires either a substantial population of stars, an actively accreting central object, or both. JWST's spectral data ruled out simple explanations like a small starburst temporarily flaring above its true mass. The energy output was too sustained, too structured, and too intense to be dismissed as a fleeting event. When stellar population models were applied, they consistently pointed toward a large amount of mass packed into a very small space. That combination is where the problem becomes serious. In standard galaxy formation theory, mass assembly is a messy process. Gas collapses under gravity, but it does not fall straight inward like sand into a funnel. It carries angular momentum, heats up, fragments, and interacts with radiation and magnetic fields. Star formation injects energy back into the system through winds, radiation pressure, and supernova explosions. All of these processes act to puff galaxies up, especially in their early stages. Compactness is hard to maintain once mass and energy cross certain thresholds. Yet this object appears to have crossed those thresholds without expanding. When astronomers plotted the object on established size-mass diagrams, it landed far outside the normal distribution. Objects with similar inferred mass are typically several times larger. Objects with similar size are typically far less massive. This was not a small offset or a borderline case. It was an outlier by a margin large enough to raise immediate red flags. The first response was caution. Extreme results often signal hidden assumptions or systematic errors. Could the mass be overestimated? Could the size be underestimated? Teams rechecked lensing effects, resolution limits, background subtraction, and modeling assumptions. Each adjustment shifted the numbers slightly, but none brought the object back into familiar territory. The discrepancy remained. Dark matter was the next suspect. In many galaxies, especially early ones, dark matter dominates the mass budget. If this object were embedded in an unusually dense dark matter halo, that might explain how it could be massive without appearing large in visible light. But this solution introduced new problems. Dark matter halos typically extend far beyond the visible component. They do not concentrate mass tightly at small radii in a way that would explain the observed compactness. Even an extreme halo could not easily reconcile the size-mass mismatch without violating constraints from simulations. Another idea was that the object represents a phase rather than a stable structure. Perhaps this is what a galaxy looks like at a very brief moment after rapid collapse, before feedback processes blow material outward. In that case, JWST may be catching an extremely short-lived configuration that was previously unobservable. This is an attractive idea because it preserves existing physics while explaining rarity. But short-lived phases leave signatures. Rapid collapse tends to generate turbulence, asymmetries, and signs of instability. Feedback-driven expansion leaves traces in gas kinematics and emission line profiles. So far, those signatures are weak or absent. The object appears surprisingly orderly for something that should be violently unstable. That calmness is almost as puzzling as the compactness itself. Feedback suppression is another possibility. If for some reason star formation feedback or radiative pressure is less effective in this system, mass could accumulate without driving expansion. However, suppressing feedback requires specific conditions. The gas would need to cool efficiently while avoiding fragmentation. Radiation would need to escape without coupling strongly to surrounding matter. These conditions are difficult to sustain, especially in the early universe where star formation is typically intense and chaotic. The object also lacks clear evidence of having recently undergone major mergers. Mergers can concentrate mass temporarily, but they usually leave behind distortions, tidal features, or multiple components. JWST's data do not show obvious signs of such interactions. The system appears singular and internally coherent. This raises a deeper issue. The size-mass relationship is not just an observational trend. It is an emergent property of gravity, thermodynamics, and angular momentum conservation. Breaking it means that at least one of those ingredients is behaving differently than expected. Either gravity is acting under unusual conditions, energy is being redistributed in an unexpected way, or the object is not what it appears to be. Some researchers have suggested that the light may not be tracing stars in the usual sense. If a significant fraction of the emission comes from non-stellar processes, such as accretion onto a massive compact object, the inferred stellar mass could be misleading. But even accretion-driven systems obey size-mass constraints of their own. Extremely luminous accreting objects tend to influence their surroundings strongly, creating extended emission regions. Again, those extensions are not clearly observed. The environment adds another layer of tension. A compact, massive object should exert strong gravitational influence on nearby gas and galaxies. One might expect inflows, disturbances, or satellite structures. So far, the surrounding region appears relatively undisturbed. This could imply isolation. But isolation itself is unusual for such massive systems at early cosmic times. As comparisons expanded, astronomers searched for analogues: compact ellipticals, too old and too evolved, protogalactic clumps, too massive, dense star clusters, too luminous and too large. Each category overlapped with one property, but failed on others. The object stubbornly resisted classification. At this point, the question shifted. Instead of asking what kind of galaxy this is, researchers began asking whether the galaxy framework itself applies. It is possible that this object represents a mode of structure formation that is rare, efficient, and previously invisible. JWST's unprecedented sensitivity may have revealed a population that earlier telescopes simply could not detect. If so, the implications are significant. Size-mass relations are used to infer growth histories, merger rates, and feedback efficiency across cosmic time. An entire population of objects that violate those relations would force revisions to models of early galaxy evolution. It would suggest that matter can assemble more efficiently and more compactly than current simulations allow. The discomfort comes from how clean the violation appears. This is not a chaotic, barely resolved smudge at the edge of detectability. It is a well-measured, internally consistent object whose properties agree with each other while disagreeing with theory. That consistency makes it harder to dismiss. In astrophysics, anomalies often fade as data improves. Measurements converge, uncertainties shrink, and objects slide back into known categories. Here, improved data has done the opposite. Each refinement has sharpened the discrepancy rather than smoothing it out. The size-mass relationship is supposed to be a guidepost. This object ignores it, and that leaves only two options. Either there is physics missing from our models of early structure formation, or this object is powered by an energy source that masquerades as mass in ways we do not yet fully understand. Untangling those possibilities requires moving beyond structure and into the object's internal engine. That next step begins not with its shape, but with the light it emits and the spectral fingerprints hidden within it. Chapter 5. Spectral signatures that defy classification. With the object's extreme size-mass relationship established, astronomers turned to its spectrum. If structure raised questions, the light itself was expected to provide answers. Spectroscopy is one of the most powerful tools in astrophysics. It reveals composition, temperature, motion, and energy sources. In many cases, it resolves ambiguity that imaging alone cannot. In this case, it deepened it. JWST's instruments are particularly well suited for spectral analysis in the infrared, a regime crucial for studying distant objects whose light has been stretched by cosmic expansion. When the object spectrum was extracted, it immediately resisted straightforward interpretation. It did not resemble the spectra of typical early galaxies, nor did it match known templates of active galactic nuclei, starbursts, or compact stellar systems. The first feature astronomers examined was the overall shape of the spectrum. Broadly, spectral energy distributions reveal whether light is dominated by stars, hot gas, dust, or accretion processes. Stellar populations produce characteristic continua shaped by their age and metallicity. Accretion disks around black holes generate power law spectra with distinct emission lines. Dust reprocesses ultraviolet light into infrared wavelengths, leaving recognizable signatures. This object spectrum did not align cleanly with any of these categories. The continuum was smooth but unusually steep, suggesting a strong energy source concentrated in a narrow region. Yet it lacked the pronounced breaks typically associated with mature stellar populations. At the same time, it did not display the strong, broad emission lines commonly associated with active black holes. Narrow lines were present, but their relative strengths were unexpected. Emission lines serve as diagnostic markers. Their presence, absence, and ratios indicate what is exciting the gas. In star-forming galaxies, certain hydrogen and oxygen lines dominate. In accreting black hole systems, high ionization lines become prominent. The object exhibited a mixture that did not fit either scenario cleanly. Some lines suggested high-energy ionization, implying an intense radiation field. Others indicated relatively cool gas conditions. Reconciling these signals within a single physical model proved difficult. Attempts to fit standard star formation models required implausibly extreme parameters. Accretion-based models, meanwhile, failed to reproduce the full line set without invoking unusual geometries or obscuration. Chemical composition added another layer of inconsistency. The early universe is expected to be metal-poor. Heavy elements form in stars and are dispersed over time. Objects at this redshift typically show low metallicity signatures. This object did not show strong evidence of heavy element enrichment, which aligns with expectations. However, the lack of enrichment conflicted with its apparent energy output. Sustained high luminosity usually requires repeated star formation or efficient accretion, both of which tend to enrich the surrounding gas. Dust indicators were similarly puzzling. Dust absorbs high energy light and re-radiates it in the infrared. The object's infrared emission suggested some reprocessing, but not at levels expected for a system producing so much energy. If dust were abundant, stronger infrared excess would be present. If dust were scarce, ultraviolet emission would be stronger. The observed balance did not match either extreme. Line widths provided insight into internal motions. Broad lines indicate fast-moving gas, often associated with strong gravitational fields or energetic outflows. Narrow lines suggest calmer environments. The object's lines were relatively narrow, implying modest internal velocities. This was difficult to reconcile with its inferred mass. A massive compact object should induce high velocities in nearby gas. The absence of broadening suggested either an unusual mass distribution or that the emitting gas was decoupled from the main gravitational potential. Redshift consistency was also examined carefully. Misidentifying spectral lines can lead to incorrect distance estimates, which would cascade into errors in all derived properties. Multiple independent line identifications were tested. The redshift held. The object was where it appeared to be in cosmic time. Foreground contamination was ruled out. The spectral features did not match those of Milky Way stars or nearby galaxies. The signal was intrinsic to the object itself. This eliminated one of the most common sources of confusion in faint object spectroscopy. Comparisons with known populations yielded limited overlap. Some compact galaxies show unusual spectra, but they typically still fall within known classes. This object did not. Its spectral signature occupied a sparsely populated region of parameter space. It was not entirely unprecedented in any single feature, but the combination was unique. This uniqueness complicates interpretation. Astrophysical classification relies on patterns. When an object fits no pattern cleanly, it forces either the creation of a new category or the expansion of existing ones. Both options carry consequences. New categories imply new formation pathways. Expanded categories require revising assumptions about how common certain processes are. One hypothesis considered was that the spectrum represents a transitional phase. Perhaps the object is caught between dominant energy sources. If star formation is shutting down while accretion is turning on, or vice versa, the resulting spectrum might appear hybrid. However, transitional phases are expected to be brief and often chaotic. The object's spectral coherence suggested something more stable. Another possibility is geometric complexity. If energy sources are deeply embedded or partially obscured, observed spectra can be misleading. Orientation effects can hide or dilute certain features. While this could explain some discrepancies, it would require fine-tuned geometry to suppress expected signatures without introducing others. The spectral data also constrain temperature. Certain line ratios indicate gas temperatures that are difficult to achieve without strong heating mechanisms. Yet those same mechanisms should leave additional spectral imprints that are absent. This internal inconsistency suggests that current models may be incomplete rather than merely misapplied. As analysis continued, a pattern emerged. The object consistently appeared more efficient than expected. It produced more energy per unit mass, remained more compact, and exhibited more order than comparable systems. Efficiency is not forbidden by physics, but it is constrained. Exceeding those constraints across multiple dimensions signals that something fundamental may be missing from the picture. JWST's role here is critical. Previous telescopes lacked the sensitivity and spectral resolution to detect and dissect such faint objects. Without this data, the object might have been misclassified or missed entirely. With it, the problem becomes unavoidable. Spectroscopy does not merely describe what an object looks like, it encodes how it works. In this case, the encoding does not decode cleanly. The light carries information that does not map neatly onto established physical processes. This does not mean the object violates known laws. It means that known laws, as currently modeled, may not capture the full range of outcomes possible under early universe conditions. Spectral anomalies often precede theoretical advances. They highlight regimes where assumptions break down. At this stage, the question is no longer whether the object is unusual. That is established. The question is whether it represents a rare outlier or the visible tip of a broader population. If similar objects exist, their collective impact on early cosmic history could be substantial. Answering that question requires looking beyond the object itself and examining its implications for population statistics and cosmological expectations. Before that can happen, one more fundamental issue must be addressed: whether the object's energy output can be sustained over time or whether it represents a transient state. That question leads directly to considerations of stability, longevity, and internal balance, which form the focus of the next section. Chapter 6: Stability, Longevity, and the Problem of Sustained Energy Output. Once the object's unusual spectral characteristics were established, attention shifted to a more fundamental question: whether such an object can exist in a stable state over meaningful cosmic time. Observations capture a moment, but interpretation depends on whether that moment represents a fleeting phase or a long-lived configuration. For an object this compact, luminous, and difficult to classify, stability is not a secondary concern. It is central to determining what the object actually is. Astrophysical systems are constrained by balance. Gravity pulls matter inward, while various forms of pressure and energy output push outward. In stars, this balance is achieved through nuclear fusion. In galaxies, it is distributed across stellar populations, gas dynamics, and dark matter halos. In accreting black holes, radiation pressure competes with gravity at the smallest scales. Any object emitting large amounts of energy must satisfy these balances, or it will rapidly change form. The object observed by JWST presents a challenge because its inferred energy output is high relative to its apparent mass and size. This raises immediate concerns about how it avoids rapid collapse, dispersal, or runaway growth. If the energy source is short-lived, the object could represent a transient event. If it is long-lived, existing models must explain how equilibrium is maintained. One possibility is that the object is undergoing a brief burst of activity. Star formation bursts, accretion flares, and merger-driven episodes can temporarily elevate luminosity. However, such events usually leave signatures of dynamical disturbance. Gas flows become chaotic, spectra broaden, and structures appear irregular. The JWST data do not show strong evidence of violent instability. The object's morphology appears coherent, and its spectral features are internally consistent rather than erratic. This coherence suggests that the energy output is not purely explosive or transient. Instead, it may reflect a quasi-steady state. Maintaining such a state requires regulated inflow and outflow of energy and matter. In galaxies, regulation is achieved through feedback processes. Star formation heats gas, slowing further collapse. Accretion onto black holes generates radiation and outflows that limit additional inflow. These feedback loops prevent unchecked growth. For this object, identifying the feedback mechanism is difficult. If stars are responsible for the energy output, their numbers appear insufficient to sustain the observed luminosity over extended periods. If a black hole is involved, the lack of strong accretion signatures complicates that explanation. Feedback without clear drivers challenges conventional understanding. Radiation pressure is another factor. High luminosity can push against infalling material, creating an effective cap on energy production. This limit is well defined for black hole accretion, known as the Eddington limit. Exceeding it for extended periods is theoretically possible under certain conditions, but it typically produces observable consequences, such as strong winds or anisotropic emission. These features are not clearly present. The compactness of the object intensifies the problem. Smaller systems reach critical densities more quickly, gas heats rapidly, radiation escapes more efficiently, and gravitational potentials steepen. These factors usually make small systems less stable at high energy output, not more. The fact that this object appears both compact and luminous contradicts naive expectations. Longevity also intersects with cosmic timing. The object is observed at a relatively early epoch in the universe. There has been limited time for repeated cycles of formation, destruction, and reassembly. Whatever configuration exists must have arisen quickly and persisted long enough to be observed. This places constraints on formation timescales and survival mechanisms. One proposed resolution is that the object is supported by a substantial dark matter component. Dark matter contributes gravitational binding without participating in radiative processes. A deep dark matter potential could stabilize the system, allowing visible matter to behave unusually without dispersing. This would help explain narrow spectral lines and structural coherence despite high inferred mass. However, dark matter alone cannot generate luminosity. It can only provide the gravitational framework. The energy source must still be baryonic. The challenge is therefore to reconcile a dark matter-dominated structure with baryonic processes that are both efficient and regulated. Thermal balance offers additional insight. The object's spectral features imply specific gas temperatures. These temperatures must be maintained against cooling processes. In small systems, cooling is usually efficient, leading to rapid star formation or collapse. Preventing runaway cooling requires either continuous heating or suppressed cooling channels. Both scenarios imply fine-tuned conditions. Suppressed cooling could occur if the gas composition is extremely primitive. Low metallicity reduces cooling efficiency, allowing gas to remain hot and diffuse longer. This aligns with some spectral indications. However, even primordial gas cools through molecular hydrogen and other channels. Completely halting cooling is difficult. Continuous heating implies a persistent energy source. If this source is accretion-driven, it must operate in a regime that avoids producing expected signatures. If it is stellar, it must involve an unusual initial mass function or stellar configuration. Both possibilities strain standard assumptions. Gravitational stability is another constraint. Compact systems are vulnerable to tidal forces, particularly in dense environments. The object's survival implies either a benign environment or a robust internal binding. Earlier analysis suggests it is not currently undergoing strong tidal disruption. This supports the idea of a stable orbit or isolated location, but does not explain internal equilibrium. Timescale arguments further complicate interpretation. The observed configuration must last long enough to be statistically detectable. If such objects were extremely short-lived, JWST would be unlikely to observe even one. The detection therefore implies either that the phase is longer than expected or that such objects are more common than previously thought. This introduces population-level implications. A single anomaly could be dismissed as rare. A stable object implies a viable formation pathway. If viable, it may operate elsewhere. Stability therefore transforms the object from a curiosity into a potential class representative. Numerical simulations are beginning to explore these regimes. Early results suggest that under certain initial conditions, compact systems can maintain high energy output without catastrophic instability. These conditions often involve low metallicity, high gas density, and specific angular momentum distributions. While promising, such simulations remain exploratory and sensitive to assumptions. The difficulty is not that stability is impossible, but that it is unexpected given prior models. This distinction matters. Astrophysics has repeatedly encountered stable configurations that were initially thought unlikely. Once mechanisms are identified, they often become integrated into broader theory. At present, the object's apparent stability serves as a constraint rather than an explanation. Any successful model must account for sustained energy output, compact structure, spectral coherence, and survival over time. Partial explanations are insufficient. The system behaves as if it occupies a narrow but real region of parameter space. JWST does not observe change over time for this object. It provides a snapshot. Stability is inferred indirectly through consistency and plausibility arguments. This is a limitation, but also a common situation in deep cosmology. Time domain information at these distances is inaccessible. What can be said is that the object does not appear to be in the midst of destruction. There are no clear signs of dispersal, collapse, or explosive transition. Whatever processes govern it are operating in a balanced regime. This balance challenges existing classifications. Objects that are too luminous, too compact, or too stable often force revisions to theoretical frameworks. The problem is not to label the object prematurely, but to understand what physical principles allow it to exist at all. This leads to a broader question: whether current models of early structure formation adequately explore extreme but allowed configurations, or whether entire regions of parameter space have been neglected. The object suggests the latter may be true. Stability in this context is not reassurance. It is a problem statement. It indicates that the universe is capable of sustaining configurations that have not been fully anticipated. Understanding how requires revisiting assumptions about feedback, cooling, and the interplay between dark matter and baryons. The next step is therefore not to focus on the object alone, but to situate it within cosmological expectations. How many such objects should exist? Where should they appear? And why have they not been seen before? These questions shift the discussion from individual physics to population statistics and cosmological models, which is the focus of the next section. Chapter 7: Rarity, Selection Effects, and Why This Object Appeared Now. With the object's internal stability established as plausible, the discussion moves outward to a broader question: how rare this object actually is. Rarity is not determined solely by how many examples are known. It is shaped by detection limits, survey strategies, and the assumptions that guide observational searches. An object may appear unique not because it is singular, but because it occupies a region of parameter space that has been poorly explored. JWST's discovery does not imply that such objects suddenly formed. It implies that the observational window capable of revealing them has only recently opened. Previous telescopes lacked the combination of sensitivity, angular resolution, and infrared coverage required to identify compact, faint, and distant systems with unusual spectral properties. As a result, entire categories of objects may have existed undetected. Selection effects play a central role. Astronomical surveys are optimized to find specific kinds of sources. Bright galaxies, quasars, and extended structures are easier to identify than compact systems with modest luminosity. Many surveys rely on color cuts, size thresholds, or emission line criteria that implicitly exclude objects that do not resemble known populations. An object that falls between categories can be filtered out at early stages of data processing. JWST operates differently. Its deep field observations are designed to push beyond conventional selection boundaries. Rather than targeting predefined classes, they record everything above a sensitivity threshold and allow classification to occur afterward. This approach increases the likelihood of detecting objects that do not fit existing templates. The object in question benefits directly from this strategy. Rarity must therefore be interpreted cautiously. The fact that only one such object has been identified does not establish its intrinsic scarcity. It establishes that at least one exists, and that the observational regime required to detect it has only recently been accessed. Statistical conclusions based on a single detection are necessarily provisional. Another factor is cosmic volume. JWST's deepest observations probe relatively small regions of the sky. Even when observing to great distances, the total volume surveyed is limited. Rare objects may exist in larger numbers across the universe, while remaining sparsely sampled in current datasets. As survey coverage expands, the apparent uniqueness of such objects may diminish. Detection probability also depends on evolutionary timing. If the object represents a particular phase in cosmic evolution, its visibility window may be narrow. Objects that exist only during specific conditions may be common in time, but rare in observation. JWST captures a snapshot across cosmic history, but that snapshot is unevenly distributed across epochs. There is also the issue of surface brightness. Compact objects with moderate total luminosity can evade detection because their light is concentrated into small areas that blend with noise or foreground contamination. JWST's resolution mitigates this effect, but does not eliminate it entirely. Similar objects may still be present below current detection thresholds. Foreground confusion further complicates detection. At faint magnitudes, distinguishing distant objects from nearer stars becomes increasingly difficult. Statistical methods help, but they are imperfect. Some candidates may be misclassified or overlooked. This biases samples against the most extreme and ambiguous systems. The object's discovery also reflects changes in analysis methods. Advances in data processing, machine learning, and statistical modeling allow astronomers to identify subtle patterns that were previously inaccessible. Re-examination of archival data with modern techniques has already led to new discoveries. It is likely that additional objects of this type exist in existing datasets but have not yet been recognized. Rarity must therefore be disentangled from novelty. The object is novel in that it challenges expectations. Whether it is rare in a physical sense remains an open question. Establishing its frequency requires systematic searches explicitly designed to find similar systems. Theoretical expectations influence perceived rarity as well. Models that predict few or no such objects encourage interpretations that treat discoveries as anomalies. If models are incomplete, observations will appear surprising by definition. Adjusting models can transform anomalies into expected outcomes. This feedback between theory and observation is central to cosmology. Observations constrain models, but models also shape how observations are interpreted. The object's discovery forces reconsideration of both detection strategies and theoretical priors. Importantly, rarity does not diminish significance. Even genuinely rare objects can have outsized implications if they occupy extreme regions of parameter space. Such objects test the boundaries of physical laws and formation scenarios. They reveal what is possible, not merely what is typical. In this case, the object's existence demonstrates that compact, energetically efficient systems can form and persist under early universe conditions. Whether this occurs frequently or rarely is secondary to the fact that it occurs at all. As JWST continues to observe, the sample size will grow. Additional detections or confirmed absences will refine estimates of abundance. Until then, conclusions about rarity must remain provisional. The key point is that the object's appearance now reflects a convergence of observational capability, survey strategy, and analytical sophistication. It is less a sudden cosmic event than a delayed recognition of something that has likely existed for billions of years. This realization reframes the discovery. The object is not necessarily an exception to cosmic history, but a previously unseen participant in it. Understanding its place requires integrating it into population-level models rather than treating it as an isolated case. That integration depends on how such objects fit within broader theories of structure formation. The next section therefore examines how this discovery interacts with existing cosmological models and what adjustments may be required to accommodate it. Chapter 8: Tension with standard models of early structure formation. With questions of rarity set aside, the object's broader significance becomes clearer when placed against standard models of how structure forms in the early universe. These models are not speculative in the casual sense. They are the result of decades of theoretical development, numerical simulation, and observational testing. They successfully reproduce large-scale cosmic structure, galaxy distributions, and many properties of early galaxies. The difficulty arises at the smallest and most extreme scales, where assumptions that work well on average begin to strain. In the prevailing framework, structure formation proceeds hierarchically. Small dark matter halos form first, drawing in gas. That gas cools, fragments, and forms stars. Over time, halos merge, galaxies grow, and complexity increases. This sequence is not rigid, but it establishes expectations about timing, scale, and efficiency. Compact, highly energetic objects are expected to appear only after sufficient mass has accumulated and feedback processes have shaped their environments. The object observed by JWST sits uncomfortably within this picture. Its inferred properties suggest that it reached a high level of organization and energy output at a point when standard models predict inefficiency. Early halos are expected to struggle with gas cooling, fragmentation, and retention. Radiation from the first stars and the background ionizing field should suppress collapse in small systems. Yet this object appears to have overcome those barriers. One source of tension lies in mass thresholds. Simulations indicate that below a certain halo mass, star formation becomes sporadic or fails entirely. Gas is heated, expelled, or prevented from condensing. Objects below this threshold should remain dark or marginal. The JWST object appears to violate this expectation, either by forming stars, sustaining accretion, or generating luminosity more efficiently than models allow. Another issue involves feedback. Feedback processes are central to regulating growth. They prevent small systems from becoming too bright or too dense too quickly. Supernova explosions, stellar winds, and radiation pressure all act to disperse gas. In larger systems, deep gravitational potentials counteract these effects. In smaller systems, feedback is expected to dominate. The observed object does not show clear evidence of disruptive feedback despite its energy output. This suggests one of two possibilities. Either feedback operates differently under early universe conditions, or the object's energy source is not governed by the same feedback loops assumed in standard models. Both possibilities imply that key processes are being oversimplified or mischaracterized in current simulations. Timing also matters. The object appears at a cosmic epoch when models predict limited chemical enrichment. Low metallicity affects cooling rates, star formation efficiency, and dust production. While low metallicity can delay fragmentation, it also constrains sustained luminosity. Reconciling early appearance with high efficiency requires carefully balanced conditions that simulations rarely produce naturally. Angular momentum presents another constraint. Gas collapsing into halos typically carries angular momentum that leads to extended disks rather than compact concentrations. Forming a small, dense system requires mechanisms to shed or redistribute angular momentum efficiently. Such mechanisms exist, but are usually associated with mergers or large-scale instabilities. There is little evidence that this object is the product of recent violent interactions. Dark matter physics enters the discussion as well. Standard cold dark matter models predict a large number of small halos, many of which remain dark. This creates the so-called missing satellites problem. Objects like this one complicate the issue further. If small halos can host efficient luminous systems under certain conditions, then the distinction between dark and luminous halos becomes less clear. Some alternative dark matter models predict different small-scale behavior. Warm dark matter, self-interacting dark matter, and other variants modify halo structure and formation timing. While the JWST object does not directly point to any specific alternative, it highlights the sensitivity of small-scale outcomes to underlying physics. Importantly, the tension is not catastrophic. Large-scale cosmology remains intact. The issue is localized to extreme regimes that were already recognized as uncertain. The object occupies a boundary region where models are least constrained and most dependent on assumptions. This distinction matters. When observations contradict well-tested predictions, theories must be revised. When they probe poorly constrained regimes, they refine rather than overturn frameworks. The object appears to belong to the latter category. It exposes gaps rather than failures. Nevertheless, these gaps are consequential. Small-scale structure formation influences reionization, early heating, and the build-up of galaxies. Even a modest population of objects like this could affect cosmic timelines. Ignoring them risks systematic error. The response from the modeling community has therefore been cautious but active. New simulations are being designed to explore parameter spaces that were previously neglected. These include extreme gas densities, unusual angular momentum distributions, and non-standard feedback prescriptions. The goal is not to force models to fit a single object, but to understand whether such outcomes are natural under certain conditions. This process illustrates how observations drive theoretical refinement. JWST did not falsify structure formation theory. It exposed an edge case that theory must now accommodate. Whether accommodation requires minor adjustment or deeper revision remains to be seen. What is clear is that the object cannot be dismissed as irrelevant. Its existence places a concrete data point at the edge of possibility. It defines a constraint that future models must satisfy. The broader implication is that the early universe may have been more diverse in its outcomes than simplified narratives suggest. Multiple pathways to compact, energetic systems may have coexisted, even if only a few were realized. Understanding which pathways are viable requires moving beyond individual cases and examining their cumulative impact. This shifts the focus from formation mechanics to consequences. If such objects exist, what do they do to their surroundings and to cosmic evolution as a whole? That question directs attention to the object's potential role in early cosmic processes, which forms the subject of the next section. Chapter 9. Implications for reionization and early cosmic heating. Having established the tension between this object and standard formation models, the next step is to assess its broader consequences. In early cosmology, individual objects matter not only for what they are, but for what they do. The universe at these epochs was highly sensitive to sources of energy. Small changes in the population of luminous systems could alter thermal history, ionization state, and the pace of structure formation. The object observed by JWST raises precisely these questions. One of the most consequential processes in early cosmic history is reionization. After the universe cooled enough for neutral hydrogen to form, it remained largely opaque to ultraviolet light until the first luminous sources began emitting high-energy radiation. These sources gradually reionized the intergalactic medium, transforming the universe into the transparent state observed today. Identifying which objects contributed to this process is a central goal of modern cosmology. Standard models attribute reionization primarily to early galaxies composed of massive, short-lived stars. These stars emit copious ultraviolet photons capable of ionizing hydrogen. Quasars and accreting black holes also contribute, but are generally thought to be less numerous at the earliest times. The relative importance of different sources depends on their abundance, luminosity, and ability to allow ionizing radiation to escape into intergalactic space. The JWST object complicates this picture. Its inferred energy output suggests that it could produce significant ionizing radiation, yet its structure does not resemble typical star-forming galaxies. If such objects are powered by unconventional stellar populations or compact accretion processes, their ionizing efficiency per unit mass could differ substantially from standard assumptions. Efficiency matters. Reionization models rely on estimates of how many photons escape from galaxies into the surrounding medium. Dense gas and dust can trap radiation, reducing effectiveness. The object's compactness and low apparent dust content suggest that radiation escape could be relatively efficient. Even if such objects are rare, their contribution per object could be disproportionate. Cosmic heating is another consideration. Before and during reionization, energy injection raises the temperature of intergalactic gas. This heating influences later structure formation by suppressing gas collapse into small halos. Objects capable of sustained energy output at early times could accelerate heating, altering the abundance of low-mass galaxies that form later. The timing implied by JWST observations is significant. The object appears at an epoch when reionization was likely still underway or approaching completion. Its presence suggests that energetic systems existed earlier and perhaps in different forms than previously accounted for. This does not require rewriting reionization history, but it does introduce additional contributors that may need to be included. The spectral characteristics discussed earlier also matter here. The object's radiation appears to span a range of energies. Depending on the hardness of its spectrum, it could ionize not only hydrogen but also helium, which requires higher energy photons. Helium reionization is usually associated with later quasars. If objects like this contribute earlier, the thermal and ionization history could be more complex. There is also the issue of spatial distribution. Reionization is not uniform. It proceeds in patches around sources, gradually overlapping. Compact, isolated objects could create localized ionized regions that expand over time. The morphology of reionization depends on the clustering and lifetimes of sources. Objects that are compact but long-lived would produce different ionization patterns than short-lived starbursts. However, caution is necessary. The contribution of a single object cannot be extrapolated without population statistics. If the object represents a rare configuration, its global impact may be minimal. If it represents a previously unrecognized class, the implications are broader. Distinguishing between these possibilities requires further detections. Observationally, reionization constraints come from multiple sources, including cosmic microwave background measurements and absorption features in distant quasar spectra. These constraints limit how much early energy injection is allowed. Any new contributor must fit within these bounds. Preliminary assessments suggest that the JWST object does not violate existing constraints, but it may reduce the margin previously attributed to other sources. This redistribution of responsibility matters. If early galaxies are less efficient at producing ionizing photons than assumed, additional sources are needed. Objects like this one could help close that gap. Alternatively, if early galaxies are already sufficient, such objects may represent a secondary contribution with localized effects. The object also raises questions about feedback timing. Early heating can suppress star formation in neighboring halos, influencing galaxy demographics. The presence of compact energetic systems could therefore shape their surroundings indirectly. Even if their number is small, their influence could extend beyond their immediate vicinity. From a modeling perspective, incorporating such objects requires flexibility. Simulations often parameterize sources by simple luminosity functions and spectral templates. Objects that do not fit standard templates challenge this approach. They require either new categories or more continuous descriptions of source properties. The significance of this chapter is not to claim that reionization must be reinterpreted, but to show that its drivers may be more diverse than previously assumed. JWST's object highlights a class of systems that sit between established categories. Their role in early cosmic heating remains uncertain, but it cannot be ignored. As observational data accumulate, constraints will tighten. If similar objects are found at multiple redshifts, their cumulative impact can be assessed quantitatively. Until then, their implications remain conditional but important. The discussion now moves from cosmic consequences back to internal composition. Understanding what powers such an object requires examining its stellar content, or lack thereof, in more detail. That analysis forms the focus of the next section. Chapter 10. Unusual stellar content and the question of what powers the object. After considering the object's possible impact on its surroundings, the focus returns inward to the source of its energy. Any luminous astrophysical system ultimately draws its power from baryonic processes, most commonly stars, or accretion onto compact objects. Determining which of these dominates requires understanding the object's stellar content. For this system, that task has proven unusually difficult. In typical galaxies, even at high redshift, Stellar populations leave clear signatures. Integrated light shows characteristic breaks and slopes, while resolved observations reveal distributions of stellar masses and ages. These indicators allow astronomers to infer star formation histories with reasonable confidence. In this case, those indicators are weak, ambiguous, or absent. JWST's imaging suggests that the object contains few stars relative to its luminosity. The stellar component, if present, appears compact and faint. This immediately raises questions about efficiency. A system that produces substantial energy while hosting a minimal stellar population challenges conventional star formation scenarios. Either the stars are far more efficient than expected, or they are not the primary source of energy. One possibility is an unusual stellar initial mass function. If star formation favored very massive stars, the system could generate high luminosity with relatively few stars. Massive stars emit far more radiation per unit mass than low-mass stars. In the early universe, conditions may have supported such top-heavy distributions. Low metallicity environments reduce cooling efficiency, potentially biasing star formation toward higher masses. However, this explanation has limits. Massive stars are short-lived. They explode as supernovae within a few million years. Sustained luminosity would require continuous formation of massive stars, which in turn requires a steady supply of cold gas. The object's compactness and lack of clear gas reservoirs complicate this scenario. Moreover, repeated supernova explosions would likely disrupt such a small system, leaving observable signatures that are not clearly present. Another possibility is that the stellar population is older than expected. If star formation occurred early and then ceased, the remaining stars would be faint and difficult to detect. In this case, the current luminosity must come from a different source. Old stars alone cannot account for the observed energy output. This shifts attention away from stars as the dominant contributor. Accretion onto a compact object is therefore a natural alternative. Accreting black holes can produce large amounts of energy with little visible stellar accompaniment. Yet, as discussed earlier, the object lacks many of the hallmarks of active galactic nuclei. Emission lines associated with accretion are weak or absent, and there is no strong evidence of surrounding hot gas or jets. This does not exclude accretion entirely. Low luminosity or obscured accretion modes exist. Accretion could occur in a radiatively inefficient regime, producing energy in ways that are difficult to detect spectroscopically. However, such modes typically produce less observable radiation, not more. Reconciling high inferred luminosity with subtle accretion signatures remains challenging. A hybrid scenario is also possible. The object may host both a small stellar population and a compact accreting source, each contributing part of the energy budget. In this case, neither component alone would dominate observational signatures. The combined effect could produce a spectrum that appears anomalous when compared to pure models. The spatial distribution of light provides additional clues. JWST data suggests that the luminosity is centrally concentrated. This favors a compact energy source rather than distributed star formation. However, resolving such structure at extreme distances is difficult, and interpretations remain model-dependent. Chemical signatures offer indirect constraints. Stellar processes enrich gas with heavy elements over time. Accretion-driven emission does not. The object's apparent low metallicity suggests limited prior star formation. This is consistent with either an early brief star-forming episode or a system where stars never dominated energetics. The absence of dust also matters. Star formation tends to produce dust through stellar winds and supernovae. Dust absorbs and re-radiates light, altering spectral energy distributions. The object's weak dust signatures suggest either minimal star formation or efficient dust destruction. Both scenarios are plausible but carry different implications. Ultimately, the question of what powers the object remains unresolved. Each proposed explanation accounts for some observations while struggling with others. This is not unusual in frontier astrophysics. Complex systems often require combinations of processes rather than single dominant mechanisms. What is clear is that the object does not conform to simple expectations. Its stellar content, whatever its exact nature, does not scale with its energy output in the way standard models predict. This decoupling is itself informative. It suggests that early universe systems may achieve luminosity through pathways that are rare or suppressed at later times. This uncertainty underscores the importance of future observations. Deeper imaging, higher resolution spectroscopy, and comparisons with additional objects will refine constraints. For now, the object stands as a case where the usual assumptions about stars and energy generation do not apply cleanly. Understanding its power source is central to interpreting its role in cosmic history. Until that understanding is achieved, the object remains suspended between categories, resisting definitive classification. This resistance is not a failure of observation, but an indication that the space of physical possibilities is broader than previously mapped. The next section turns to how such an object might form in the first place. Power sources address how it shines. Formation scenarios address how it came to exist at all. Chapter 11. Formation pathways that push the limits of early physics. With the question of what powers the object still unresolved, attention turns to a more foundational issue: how such an object could have formed at all. Formation is not simply a matter of assembling mass. It involves timing, environment, and the interplay of competing physical processes. For an object that appears compact, efficient, and anomalous so early in cosmic history, standard formation pathways offer limited guidance. In conventional models, early galaxies emerge gradually. Dark matter halos collapse first, drawing in baryonic gas. That gas cools, fragments, and forms stars. Over time, feedback from those stars regulates further growth. This sequence establishes expectations about scale and pace. Objects that deviate from it must either exploit rare conditions or follow alternative routes. One proposed pathway involves direct gas collapse. Under specific circumstances, large amounts of gas can collapse into a compact configuration without fragmenting into stars. This requires suppressing cooling mechanisms that normally promote fragmentation. Low metallicity plays a role, as heavy elements enhance cooling efficiency. In extremely primitive environments, gas may remain warm enough to avoid breaking apart, allowing it to flow inward coherently. Such conditions are theoretically plausible in the early universe. Regions with strong background radiation can dissociate molecular hydrogen, removing a key cooling channel. In these environments, gas collapse can proceed rapidly and centrally. The result may be a dense core capable of powering significant luminosity without an extensive stellar population. However, direct collapse scenarios are sensitive to initial conditions. They require a narrow balance between radiation intensity, gas density, and angular momentum. Small deviations lead to fragmentation or dispersal. Producing such conditions repeatedly is challenging, but producing them occasionally is not impossible. The JWST object may represent one such outcome. Another possibility involves accelerated hierarchical assembly. Rather than growing smoothly, the object may have formed through a sequence of rapid mergers among small halos. If mergers occur before significant star formation begins, gas can be funneled inward efficiently. This can produce compact configurations earlier than average. However, mergers typically leave dynamical signatures and increase angular momentum, which must then be dissipated. Angular momentum remains a persistent obstacle. Gas collapsing into halos naturally acquires rotation. Shedding that rotation is necessary to achieve compactness. Mechanisms such as gravitational torques and turbulence can redistribute angular momentum, but their efficiency varies. The object's compact structure suggests that angular momentum loss was unusually effective. Environmental isolation may have contributed. If the object formed in a region with limited external disturbance, internal processes could dominate. Isolation reduces tidal disruption and allows rare configurations to persist. However, isolation alone does not explain efficient energy production. Primordial conditions also matter. Density fluctuations in the early universe were not uniform. Regions of slightly higher density collapsed earlier and faster. Objects forming in these regions could reach advanced states before others. This bias can produce early outliers without requiring new physics. The formation timeline implied by observations is tight. There is little room for prolonged inefficiency. Whatever process operated must have been fast and effective. This constraint rules out many slow growth scenarios. Importantly, none of these pathways require violating known physical laws. They exploit extreme but allowed conditions. The difficulty lies in their rarity and sensitivity. Models must explain not just that such an object can form, but that it can form often enough to be observed. This distinction matters. A formation pathway that produces one object in a trillion may be physically possible, but cosmologically irrelevant. The JWST detection suggests that either the probability is higher or that observational biases favor such objects. Current simulations struggle to explore these extremes comprehensively. Computational limits often force simplifications that smooth over rare configurations. As a result, models may underpredict objects that occupy narrow regions of parameter space. The object therefore serves as a boundary marker. It defines a region where formation is difficult but not forbidden. Understanding that region requires targeted modeling rather than broad averages. As theoretical work adapts, formation scenarios will be refined. Some will be ruled out, others will gain support. For now, the object remains an existence proof that early cosmic conditions could produce structures more compact and efficient than standard narratives imply. Formation alone does not resolve classification. An object's origin influences its present behavior, but does not dictate its category. To place this object within a broader framework, its relationship to known populations must be examined directly. That comparison, rather than speculation about origin alone, is the focus of the next section. Chapter 12. Why this object does not fit existing categories. With potential formation pathways outlined, the remaining challenge is classification. Astronomical classification is not merely a naming exercise. Categories encode physical assumptions about how objects form, how they evolve, and what processes dominate their behavior. When an object cannot be placed confidently into an existing category, it indicates that those assumptions may be incomplete. The object identified by JWST presents exactly this problem. At first glance, the most natural classification would be a galaxy. It appears to be a gravitationally bound system. It emits sustained radiation, and it exists at a cosmological distance consistent with early structure formation. Yet galaxies, even the smallest known examples, follow certain scaling relationships. They exhibit a connection between stellar mass, size, and luminosity. In this case, those relationships break down. The object's inferred energy output is too large for the apparent paucity of stars, and its compact structure does not resemble even ultra-faint dwarf galaxies known from later epochs. The alternative classification as a star cluster also fails under closer examination. Star clusters can be extremely compact and faint, and some globular clusters approach the lower limits of galactic luminosity. However, star clusters are dominated by their stellar mass and lack substantial dark matter halos. Their internal dynamics can be explained entirely through visible matter. The stability and inferred mass of this object suggest a gravitational potential that exceeds what stars alone could provide. In addition, star clusters do not typically form at such early cosmic times in isolation, nor do they sustain significant energy output beyond what stellar populations allow. Quasar, or active galactic nucleus classifications, introduce a different set of conflicts. Accreting black holes can generate enormous luminosity from compact regions, making them attractive candidates for explaining the object's energy output. However, quasars exhibit characteristic observational signatures. These include broad emission lines, high ionization features, and often variability linked to accretion processes. The object lacks these defining traits. Its spectrum does not align with known quasar templates, and its emission appears too structured and restrained to reflect typical accretion-driven systems. Intermediate categories offer little relief. Low luminosity active galactic nuclei still require host galaxies with detectable stellar populations and gas reservoirs. Ultra-compact dwarf galaxies occupy a transitional space between star clusters and galaxies, but they are generally products of tidal stripping and appear at much later times. Their formation histories and environments do not match the conditions implied by this object's redshift and isolation. What complicates matters further is that the object does not appear chaotic or transitional. Objects caught in brief evolutionary phases often display irregular morphologies, disturbed kinematics, or inconsistent spectral features. This system does not. Its structure appears coherent, its spectral characteristics are internally consistent, and its inferred stability suggests it is not in the midst of rapid transformation. This argues against interpreting it as a short-lived anomaly. The difficulty is therefore not that the object resembles nothing known, but that it resembles multiple known classes, partially while fully satisfying none. It has the compactness of a star cluster, the gravitational depth associated with galaxies, and the energetic efficiency often linked to accretion, yet it does not behave like a straightforward example of any of these. This hybrid nature exposes limitations in classification schemes that assume clean separations between object types. Classification also depends heavily on evolutionary context. Many categories are defined based on objects observed in the later universe, where physical conditions differ markedly from those at early times. Applying those categories retroactively assumes that early universe systems behaved as scaled-down versions of later ones. The object challenges this assumption. It suggests that early cosmic environments may have supported configurations that no longer form or form only under exceptional circumstances. This ambiguity has practical consequences. Observational surveys often rely on automated classification pipelines, tuned to recognize known categories. Objects that fall between definitions risk being filtered out, misclassified, or ignored as noise. The identification of this object required deliberate attention to outliers and a willingness to question initial assumptions. Its discovery therefore reflects not only instrumental capability, but methodological openness. From a theoretical standpoint, classification failure is informative. It indicates that models may be overly constrained by expectations derived from well-studied populations. If nature permits configurations outside those expectations, then theory must expand to accommodate them. This does not imply discarding existing categories, but recognizing that they may not exhaust the space of physical possibilities. The object may represent a genuinely new class of early universe systems, characterized by extreme compactness, low stellar content, and efficient energy production. Alternatively, it may be an extreme manifestation of a known class, operating under conditions rarely sampled by observations or simulations. Distinguishing between these interpretations requires additional examples. A single object can expose a problem, but it cannot define a population. For now, classification remains intentionally unresolved. Assigning a definitive label would imply understanding that does not yet exist. Instead, the object is best described through its measured properties and the ways in which those properties resist existing frameworks. This descriptive approach avoids premature conclusions while preserving the significance of the anomaly. Historically, moments like this have preceded major revisions in astrophysical understanding. Objects that initially defied classification often became central once their underlying physics was understood. The current ambiguity places this object within that tradition. It is not an outlier to be dismissed, but a boundary case that tests the robustness of current taxonomies. Ultimately, the inability to classify the object cleanly is not a failure of observation. It is a signal that the universe, particularly at early times, may have produced structures that fall outside simplified narratives. Recognizing and studying such cases is essential to building a more complete picture of cosmic history. The final question is, therefore, not what to call the object, but what its existence implies about the range of structures the universe can produce. That question extends beyond classification and leads directly to considerations of future discoveries and how JWST may continue to reshape expectations. Chapter 13. What this object suggests about the limits of observation. With classification unresolved, the discussion shifts to a different but equally important issue. What this object reveals about the limits of observation itself. The difficulty in interpreting the object is not solely a theoretical problem. It is also an observational one. The object exists at the edge of what current instruments can reliably detect and characterize, and that position shapes how it is understood. JWST was designed to extend observational reach, not eliminate uncertainty. Every measurement carries limits set by sensitivity, resolution, background noise, and modeling assumptions. Objects that sit comfortably above detection thresholds are relatively straightforward to study. Objects near those thresholds are not. This system belongs firmly in the latter category. One challenge lies in signal-to-noise. At extreme distances, even JWST collects limited photons from faint sources. Spectral features that would be clear in brighter systems become subtle. Small uncertainties in background subtraction or calibration can influence interpretation. While the object's detection is secure, many of its inferred properties depend on marginal signals rather than dominant ones. Resolution is another constraint. JWST's angular resolution is exceptional, but at cosmological distances, even that resolution corresponds to large physical scales. Structures that are compact on galactic scales may be unresolved or only barely resolved. This limits the ability to distinguish between centrally concentrated light and distributed emission. As a result, conclusions about morphology remain probabilistic rather than definitive. Foreground contamination also becomes more problematic at faint levels. Stars within the Milky Way can mimic distant compact objects in color and brightness. Statistical techniques reduce this risk, but they do not eliminate it entirely. Each object identified near the detection limit requires careful validation to ensure it is not a projection effect or rare foreground alignment. Distance estimation introduces further uncertainty. Redshift determination relies on identifying spectral features that may be weak or blended. While multiple lines support the object's inferred distance, small errors propagate into size, mass, and luminosity estimates. At these extremes, even modest shifts can alter interpretation significantly. Model dependence compounds these issues. Translating observed light into physical properties requires stellar population models, assumptions about dust, and prescriptions for gas physics. These models are calibrated using better studied systems. Applying them to an object that may lie outside known regimes introduces systematic uncertainty. The object may not violate physics, but it may violate model applicability. Selection effects also shape what is observed. JWST's deeper surveys cover limited sky areas. They preferentially detect objects that meet certain criteria, even if unintentionally. The object's discovery reflects where JWST looked and how data were processed. Similar objects may exist outside surveyed regions or fall below detection thresholds due to orientation or environment. This raises an important point. Observational absence cannot be equated with physical absence. The fact that few such objects are known does not mean few exist. It means few have been detected under current conditions. As observational strategies evolve, the apparent population may change. The object, therefore, functions as both a discovery and a diagnostic. It highlights where observational capability intersects with theoretical expectation. It reveals not only what exists, but what can be recognized given present tools. This perspective tempers interpretation. The object should not be treated as a definitive challenge to cosmology, nor as an anomaly that demands immediate explanation. Instead, it should be viewed as an indicator that exploration has reached a regime where uncertainty is intrinsic. Historically, similar situations have occurred. Early quasars were initially puzzling because their luminosities seemed impossible. Only later did understanding of accretion physics mature enough to accommodate them. In those cases, the issue was not that observations were wrong, but that the framework used to interpret them was incomplete. The same may be true here. The object may eventually fit naturally into an expanded model of early universe structure. Alternatively, it may remain a rare configuration that tests the boundaries of possibility. Both outcomes require acknowledging observational limits rather than overstating conclusions. JWST's role is crucial but finite. It provides unprecedented access, but it does not eliminate ambiguity. Future instruments with greater sensitivity, resolution, or complementary wavelength coverage will refine or revise current interpretations. Until then, uncertainty must be integrated into analysis rather than treated as an obstacle. Understanding these limits also informs how future surveys should be designed. Objects like this one motivate targeted searches for compact, faint systems and the development of analysis methods optimized for edge cases. They encourage examination of data that might otherwise be dismissed as noise or outliers. The object's existence therefore reshapes expectations not only about cosmic structure, but about discovery itself. It suggests that some of the most informative systems may be those that are hardest to interpret. These systems expose gaps in both observation and theory. Recognizing this changes how significance is assigned. The value of the object lies not only in what it is, but in what it reveals about the current frontier. It marks a point where observation outruns explanation, inviting careful, incremental progress rather than decisive claims. The next section moves beyond observational limits to consider how discoveries like this influence future research priorities. The question is not simply what has been found, but how it redirects where scientists look next and what questions they consider most urgent. Chapter 14: How this discovery reshapes future search strategies. With the limits of observation clarified, the discussion naturally turns toward consequences. Discoveries like this do not merely add an entry to a catalogue. They influence how future observations are designed, what kinds of objects astronomers expect to find, and which assumptions guide data analysis. In this sense, the object's importance lies as much in how it changes behavior as in what it reveals directly. Historically, astronomical searches have been shaped by known categories. Telescopes are pointed where galaxies are expected, pipelines are tuned to identify familiar signatures, and anomalies are often filtered out as statistical noise. This approach is efficient, but it assumes that most meaningful objects resemble those already known. The JWST object exposes the limits of that assumption. One immediate implication is the need to broaden selection criteria. Objects that are compact, faint, and spectrally ambiguous are easy to miss when filters prioritize brightness, size, or well-defined emission lines. The fact that this object was detected suggests that relaxing or rethinking these criteria can reveal previously hidden populations. Future surveys are likely to incorporate more flexible classification schemes that flag outliers for closer inspection rather than discarding them. Search strategies may also shift toward parameter space exploration rather than category-driven detection. Instead of asking whether a source looks like a galaxy or a quasar, astronomers may increasingly ask whether it occupies an unusual combination of size, luminosity, and spectral slope. This multidimensional approach reduces reliance on rigid labels and increases sensitivity to unexpected configurations. The discovery also emphasizes the value of deep, small-area surveys. Wide-field surveys excel at mapping large populations but often lack the depth needed to detect extreme objects. JWST's deep fields demonstrate that rare or subtle systems can emerge only when sensitivity is pushed to its limits. Balancing depth and coverage will become an increasingly strategic decision rather than a purely technical one. Data analysis methods are likely to evolve as well. Automated pipelines are essential for handling the volume of modern astronomical data, but they are optimized for speed and consistency. Identifying objects like this one may require hybrid approaches that combine automation with targeted human inspection or adaptive algorithms trained to recognize novelty rather than conformity. Machine learning tools are particularly relevant here. Traditional models are trained on known examples and may struggle with objects outside those distributions. Future approaches may emphasize anomaly detection, allowing algorithms to flag sources that differ significantly from training data without needing to classify them immediately. This reframes unknown as a feature rather than a failure. Spectroscopic follow-up priorities may also change. Objects that resist easy interpretation in imaging data may warrant early spectroscopic attention, even if they are faint or ambiguous. This contrasts with traditional strategies that reserve spectroscopy for sources already classified as interesting. The object demonstrates that ambiguity itself can be informative. The discovery further suggests that theoretical expectations should play a less restrictive role in early filtering. When models strongly predict that certain objects should be rare or non-existent, observations inconsistent with those predictions may be downweighted or overlooked. Recognizing that models are least reliable at extremes encourages a more open-ended approach to data. There are also implications for survey design beyond JWST. Future space and ground-based observatories will build on its legacy. Decisions about wavelength coverage, resolution, and sensitivity can be informed by the kinds of objects JWST has revealed. Compact, faint systems argue for instruments capable of high resolution at low surface brightness, even if such capabilities complicate design. The object also highlights the importance of archival reanalysis. As detection strategies evolve, existing datasets may contain additional examples that were previously unrecognized. Systematic re-examination of deep field data using updated methods could expand the sample without requiring new observations. Importantly, these shifts do not imply abandoning existing search goals. Galaxies, quasars, and large-scale structure remain central to cosmology. The lesson is not that traditional categories are obsolete, but that they are incomplete. Expanding the search space increases the likelihood of encountering systems that test and refine theory. The object also influences how uncertainty is treated. Instead of being seen as a weakness, uncertainty becomes a guide. Objects with ambiguous properties signal where models and observations intersect imperfectly. Focusing on these intersections can yield disproportionate insight. From a practical standpoint, this may slow interpretation. Objects that do not fit neatly require careful analysis and resist quick conclusions. This is a cost, but it is also an opportunity. The history of astrophysics shows that some of the most important advances arose from sustained engagement with stubborn anomalies. The discovery therefore acts as a catalyst. It encourages astronomers to design searches that are sensitive to the unexpected and to treat anomalies as data-rich rather than problematic. This mindset increases the chance of uncovering new physical regimes. In this context, the object is less an endpoint than a starting point. It demonstrates that JWST is capable of revealing systems that force reconsideration of assumptions. Whether many such objects exist or only a few, their influence on research priorities will persist. The final section considers what this means at the highest level. Beyond strategy and methodology, discoveries like this shape how cosmology understands its own limits. They define where knowledge ends and exploration begins, and they invite a reassessment of what it means to map the universe with incomplete tools. Chapter 15. What this object ultimately reveals about the frontier of cosmology. At the broadest level, the significance of this object lies not in any single property, but in what its existence reveals about the current frontier of cosmology. It occupies a region where observation, theory, and classification all reach their limits simultaneously. In doing so, it exposes how much of modern cosmology depends not on definitive answers, but on managed uncertainty. Cosmology has been shaped by success at large scales. The expansion of the universe, the distribution of galaxies, and the behavior of cosmic background radiation are described with remarkable precision. These achievements create the impression that the universe is well understood. Objects like this one complicate that impression by showing that certainty fades rapidly as attention shifts to small, early, and extreme systems. The object demonstrates that the early universe was capable of producing configurations that current models did not strongly anticipate. This does not invalidate those models, but it does reveal where they are least constrained. Small-scale structure formation, feedback efficiency, and early energetic processes remain areas where assumptions dominate over direct evidence. The object marks one such assumption boundary. It also highlights the asymmetry between observation and explanation. JWST can now detect systems that theory struggles to interpret. This is a reversal of earlier eras, where theory often ran ahead of observation. The balance has shifted. The telescope reveals phenomena faster than existing frameworks can absorb them. This is not a crisis, but a characteristic phase in scientific progress. Importantly, the object does not force an immediate revision of cosmological parameters or fundamental laws. Its implications are more subtle. It suggests that the space of possible outcomes in the early universe is broader than simplified narratives imply. Some pathways may be rare, sensitive to initial conditions, or confined to narrow regions of parameter space, yet still physically real. This realization affects how absence is interpreted. If one object exists outside expectations, others may as well. The absence of widespread detection does not guarantee absence of population. It reflects observational limits, selection effects, and the fact that extreme systems may not be evenly distributed in time or space. The object also reframes how anomalies are valued. Rather than being treated as statistical curiosities, anomalies become probes of incompleteness. They indicate where additional physics, overlooked processes, or revised assumptions may be required. In this sense, the object is informative precisely because it does not fit. There is also a philosophical implication. Cosmology often seeks unifying explanations that reduce complexity. This object resists reduction. It suggests that the early universe may not have followed a single dominant developmental path, but instead explored multiple routes to structure formation, only some of which persisted. This diversity complicates modeling but enriches understanding. It implies that the universe's history cannot be fully captured by average behavior alone. Edge cases matter. They shape boundaries, define constraints, and reveal possibilities. The object also underscores the provisional nature of classification. Categories are tools, not truths. When they fail, the appropriate response is not to force alignment, but to reassess the criteria themselves. The object's resistance to labeling is therefore a productive tension rather than a deficiency. From a practical perspective, this discovery reinforces the importance of patience. Objects at the frontier require time to interpret. Data must accumulate, models must adapt, and comparisons must be made across multiple systems. Premature conclusions risk obscuring rather than clarifying significance. It also suggests that JWST's most transformative contributions may not come from confirming predictions, but from exposing blind spots. Each such exposure redirects inquiry and expands the conceptual map of the universe. The object does not close a chapter in cosmology. It opens one. It marks a point where exploration reaches conditions that challenge inherited expectations. Whether it remains unique or becomes the first of many, its role is already clear. It shows that deep space still contains structures that do not announce their nature easily. It shows that observation can outpace explanation without rendering explanation obsolete. And it shows that the universe, even at scales thought to be constrained, retains the capacity to surprise. As JWST continues to observe, similar tensions will likely emerge. Each will demand the same response: careful measurement, restrained interpretation, and willingness to revise assumptions. The object stands as an early signal of this phase of discovery. What it ultimately represents is not an endpoint, but a reminder. The smallest, faintest, and most difficult objects often carry the greatest leverage over understanding. They sit where certainty gives way to inquiry, and where inquiry defines the future direction of the field. In that sense, the object's most important contribution is not what it explains, but what it compels cosmology to confront next. Chapter 16. What comes after discovery? Open questions without closure. Even after sustained analysis, the object remains defined more by questions than by answers. This is not a failure of investigation, nor does it reflect insufficient data quality. It reflects the reality of discovery at the edge of observational and theoretical reach. When an object occupies territory where measurement precision, physical interpretation, and classification all approach their limits simultaneously, resolution does not arrive quickly. Instead, discovery marks the beginning of a longer phase of uncertainty-driven inquiry. One of the most immediate unresolved questions concerns prevalence. At present, the object stands largely alone in the data. Whether it represents a rare, almost singular configuration, or the first identified member of a broader population cannot yet be determined. Establishing prevalence requires searches explicitly designed to find similar systems, rather than relying on general-purpose surveys. This involves reanalyzing existing JWST deep fields with modified selection criteria and planning future observations that prioritize sensitivity to compact, spectrally ambiguous sources. Until such work is completed, any statement about rarity remains provisional. Closely tied to prevalence is the question of detectability. Objects like this may exist in greater numbers, but evade detection because of their compactness, faintness, or unusual spectral properties. Even with JWST, detection efficiency drops sharply near sensitivity limits. Small changes in background noise, orientation, or foreground contamination can determine whether an object is identified or missed. This means that current catalogues may underrepresent entire classes of systems that occupy extreme parameter space. Another unresolved issue is evolutionary fate. The object is observed at a specific moment in cosmic history, but its trajectory before and after that moment remains inferred rather than directly observed. It may evolve into a more conventional galaxy as stars accumulate and structure expands. It may lose energy and fade into obscurity, becoming undetectable at later times. It may merge into a larger system and disappear as a distinct entity. Each scenario carries different implications for how early universe anomalies contribute to later cosmic structure. Understanding this evolution requires modeling rather than observation alone. Simulations must explore how compact, efficient systems behave over billions of years under realistic environmental conditions. These simulations are challenging because they must resolve small scales while evolving large volumes over long timescales. As a result, the evolutionary pathways of such objects remain one of the least constrained aspects of current theory. Internal composition also remains uncertain. While constraints exist on stellar content, gas properties, and energy output, they do not uniquely identify the dominant physical processes at work. Distinguishing between exotic stellar populations, unconventional accretion regimes, or hybrid mechanisms requires higher signal-to-noise spectroscopy and broader wavelength coverage. Such observations are demanding in terms of telescope time and data quality, particularly for faint systems at high redshift. The role of dark matter introduces additional uncertainty. The object's inferred stability and compactness suggest a significant dark matter component, but its distribution and interaction with baryonic matter are not directly observable. Different dark matter models predict subtle differences in small-scale structure that could become relevant if more objects of this type are identified. At present, the object does not favor any specific alternative model, but it highlights where standard assumptions are least tested. Environmental context remains another open area. The object does not exist in isolation from cosmic structure. Its surroundings may hold clues to its formation and survival. Is it located in a region of enhanced density, intense radiation background, or unusual gravitational configuration? Are similar objects clustered, or are they spatially isolated? Answering these questions requires mapping not just individual systems, but their broader environments across multiple fields. Methodologically, the object exposes limitations in how novelty is handled. Automated pipelines excel at identifying known classes of objects, but struggle with systems that do not fit training sets. This raises the possibility that additional anomalies exist in current data, but remain unrecognized. Adapting analysis frameworks to treat ambiguity as a signal rather than a flaw will be essential as observations push further into unexplored regimes. There is also the issue of interpretive caution. Objects that resist explanation attract attention, but overinterpretation can distort understanding. The object does not yet justify claims of new physics or radical revision of cosmological models. Its significance lies in what it suggests, not in what it proves. Maintaining this distinction is critical to preserving scientific rigor. At a deeper level, the object challenges assumptions about completeness. Cosmological models often aim to describe the average behavior of matter and energy across the universe. Objects like this one demonstrate that averages do not capture the full range of outcomes. Rare or extreme configurations can exist without dominating cosmic history, yet still matter for understanding what is physically possible. This realization reshapes expectations about progress. Rather than converging toward a final closed description of the universe, cosmology appears to advance through cycles of constraint and surprise. Each new observational frontier exposes regimes where understanding is incomplete. The object occupies such a regime, serving as a reference point for future exploration. Importantly, the absence of closure is not a weakness. It is a defining feature of frontier science. The object does not demand immediate answers. It demands sustained attention, careful comparison, and incremental refinement of both observation and theory. Its value lies in anchoring questions rather than resolving them. As JWST continues its mission, similar objects may emerge, or this one may remain singular. Both outcomes are informative. Multiple detections would indicate a hidden population requiring incorporation into models. Singularity would mark an extreme but allowed configuration that defines the edge of possibility. In either case, understanding deepens. What remains constant is the role such objects play in shaping inquiry. They expose assumptions, highlight limitations, and expand the conceptual space in which cosmology operates. They remind researchers that the universe does not arrange itself for ease of classification or explanation. In this sense, the object's story does not end with analysis. It persists as an open marker within cosmological research, a point where certainty gives way to investigation. It defines not an answer, but a boundary, and boundaries are where scientific understanding advances next. Chapter 17. Why this object matters. Even if it remains singular. At this stage, it is reasonable to ask whether the object's importance depends on finding more like it. In many areas of astronomy, significance is tied to population statistics. A single detection can be dismissed as an outlier, while a class of objects reshapes theory. In this case, however, the object's relevance does not depend entirely on multiplicity. Even if it remains singular, it carries meaningful implications. Singular objects have played pivotal roles in astrophysics before. The first quasars were initially regarded as curiosities because their luminosities appeared implausible. Pulsars were once mysterious radio sources before their nature was understood. In each case, a small number of detections revealed gaps in existing frameworks. The value lay not in numbers, but in what the objects forced scientists to confront. This object functions in a similar way. It occupies a region of parameter space where expectations were weak or unexamined. Its existence demonstrates that certain configurations are physically possible, even if rare. That demonstration alone constrains theory. Models that predict such objects cannot exist at all must be revised, regardless of how infrequently they occur. The object also serves as a boundary condition. It defines a lower or upper limit on combinations of size, luminosity, compactness, and efficiency. Boundaries matter because they shape how models are constructed. Knowing that a configuration is possible forces simulations to accommodate it, even if it does not dominate outcomes. From a methodological perspective, singular objects are stress tests. They expose where assumptions break down. This object reveals how classification schemes, detection strategies, and interpretive models perform under extreme conditions. The fact that it resisted easy categorization indicates that those systems were not designed with such extremes in mind. There is also a temporal dimension to significance. The object appears at an early epoch when the universe was undergoing rapid transformation. Conditions at that time were unlike those in the later universe, and outcomes were more sensitive to initial fluctuations. A rare configuration at early times may have disproportionate influence on later structure, even if it does not persist. This is particularly relevant for processes like heating, ionization, and feedback. A small number of energetic objects could locally alter conditions, affecting neighboring systems. Even if such objects are sparse, their impact may not scale linearly with abundance. The object also informs expectations about incompleteness. If one such object exists, it is possible that others exist just beyond current detection limits. Singularity may reflect observational boundaries rather than physical rarity, treating singularity as definitive risks, underestimating hidden diversity. There is also a conceptual implication. Cosmology often relies on simplifying assumptions to manage complexity. Singular objects challenge those simplifications by demonstrating that the universe does not always conform to average behavior. Recognizing this does not undermine the utility of averages, but it cautions against treating them as exhaustive. Importantly, the object's significance is cumulative. Each unresolved question it raises interacts with others. Formation, power source, stability, and classification are not independent issues. The object sits at the intersection of these uncertainties, amplifying their combined effect. This amplification is why the object matters even in isolation. It concentrates multiple areas of uncertainty into a single case. Addressing it forces engagement with fundamental aspects of early universe physics that might otherwise remain abstract. The object also plays a role in shaping future interpretation. Once a configuration is known to exist, it changes how new data are viewed. Observations that might previously have been dismissed as noise or error may be reconsidered in light of this precedent. Singular discoveries expand interpretive openness. From a philosophical standpoint, the object reinforces a core principle of empirical science. The role of observation is not to confirm comfort, but to reveal reality. When reality resists expectation, the task is not to explain it away, but to understand why expectations were limited. This perspective reframes how progress is measured. Advancement is not always marked by resolution. Sometimes it is marked by the identification of durable questions. The object provides such questions, grounded in observation rather than speculation. Even if no additional examples are found, the object will continue to influence modeling choices, observational strategies, and theoretical priorities. It will serve as a reference point for what is possible under early cosmic conditions. If more examples are found, its role will expand. It will become the prototype for a class. If not, it will remain an extreme case that defines a boundary. Both outcomes are scientifically valuable. Ultimately, the object's importance lies in how it reshapes the landscape of inquiry. It narrows some possibilities, opens others, and clarifies where knowledge remains incomplete. Singularity does not diminish that effect. In some cases, it sharpens it. The next section turns to how this object fits into a longer historical pattern of discovery, and what its emergence says about how cosmology advances when new observational frontiers are opened. Chapter 18. A familiar pattern. How new telescopes reshape understanding. The emergence of this object follows a pattern that has repeated throughout the history of astronomy. Each time observational capability advances significantly, it reveals phenomena that existing theories did not fully anticipate. These discoveries are rarely isolated surprises. They tend to cluster around the edges of what previous instruments could detect, exposing regimes that were always present, but effectively invisible. The James Webb Space Telescope is continuing this pattern, and the object under discussion is a clear example. Earlier generations of telescopes shaped understanding by what they could see. Optical surveys favored bright, extended galaxies and luminous quasars. Radio telescopes uncovered entirely different classes of objects, such as pulsars and active galactic nuclei, that were invisible at optical wavelengths. X-ray observatories later revealed hot gas, accretion disks, and energetic processes that reshaped models of galaxy evolution. In each case, new windows did not merely refine existing knowledge. They forced revisions in how the universe was conceptualized. JWST operates in a regime that previous instruments sampled only weakly. Its infrared sensitivity allows it to see through dust, detect faint sources, and observe light from the earliest cosmic epochs. As a result, it does not simply extend known populations to higher redshift. It reveals configurations that were systematically excluded by earlier limitations. The object discussed here is not an exception to this trend. It exemplifies it. Historically, the initial response to such discoveries has often been caution mixed with skepticism. Early quasars were once debated as nearby stars with unusual properties because their inferred luminosities seemed implausible. Pulsars were initially described as potential artificial signals because their regularity defied expectation. In retrospect, these reactions reflected the boundaries of existing frameworks rather than flaws in observation. The current situation is analogous. The object does not violate physical laws, but it violates assumptions embedded in simplified narratives of early structure formation. Those assumptions were not unreasonable. They were based on the best available data at the time. What JWST has done is expose where those assumptions no longer suffice. This pattern underscores an important point. Observational progress tends to reveal complexity rather than eliminate it. Each new capability reduces uncertainty in some areas while introducing new questions in others. The universe does not become simpler as it is observed more deeply. It becomes more detailed. The object also illustrates how theory adapts incrementally. When new phenomena are discovered, they are rarely accommodated by wholesale theoretical overhaul. Instead, models expand to include additional processes, boundary conditions, or rare outcomes. Over time, what was once anomalous becomes integrated into a broader framework. The difficulty lies in recognizing which anomalies represent new physics and which reflect underexplored corners of existing physics. JWST's discoveries are still in an early phase. Patterns have not yet stabilized. Single objects can loom large simply because comparative samples are small. As more data accumulate, context will improve. Some anomalies will fade into expected variation. Others will persist and demand deeper explanation. The object under discussion may fall into either category. What matters is how the community responds. Treating such objects as nuisances to be explained away risks missing opportunities for insight. Treating them as definitive evidence of new physics risks overreach. The productive path lies between these extremes, where anomalies are taken seriously but evaluated cautiously. The object's discovery also highlights the interplay between instrumentation and interpretation. JWST did not change the universe. It changed what can be seen. This distinction is essential. Observational revolutions often appear as theoretical crises, but they are better understood as expansions of accessible reality. This perspective helps frame expectations. It is likely that additional objects with unusual combinations of properties will emerge from JWST data. Some will challenge classification. Others will strain formation models. This does not indicate failure. It indicates that exploration has reached regimes where diversity was always present but poorly sampled. The historical pattern suggests that resolution will come gradually. As similar objects are identified, comparisons will clarify which features are essential and which are incidental. Statistical analysis will replace singular emphasis. Over time, categories may be refined or new ones introduced. In this sense, the object serves as an early indicator rather than a final statement. It marks the beginning of a phase in which JWST reveals the full range of early universe outcomes, not just those that fit inherited expectations. Understanding this pattern tempers urgency. There is no need to rush to definitive conclusions. History shows that patience and accumulation of evidence are more effective than immediate reinterpretation. The broader lesson is that observational frontiers reshape understanding not by providing answers, but by changing the questions that are asked. The object forces attention toward efficiency, compactness, and diversity in early cosmic systems. These themes will likely recur as JWST continues its work. The next section examines how this object, and others like it, may influence how cosmology communicates uncertainty and revises confidence as exploration proceeds deeper into unknown territory. Chapter 19. When Data Outpaces Confidence. Rethinking Certainty in Modern Cosmology. As discoveries like this accumulate, they expose a growing tension in modern cosmology. Data are advancing faster than confidence in interpretation. This is not a failure of science. It is a predictable consequence of operating at observational frontiers, where signals are faint, samples are small, and theoretical priors were shaped by a much narrower view of the universe. The object highlighted by JWST sits squarely in this tension zone, where measurements are robust, but meaning remains unsettled. For much of cosmology's history, confidence grew alongside data. Larger surveys reduced uncertainty. Better instruments refined parameters. Models converged. This pattern reinforced the idea that progress naturally leads toward closure, but frontier observations behave differently. Instead of narrowing possibilities, they often expand them. Each new capability uncovers regimes where existing models were never strongly constrained to begin with. JWST operates precisely in such a regime. Early universe observations rely on extrapolation. Models of galaxy formation, star formation efficiency, and black hole growth were calibrated using later cosmic epochs and then projected backward. These projections were reasonable, but they were not guarantees. When JWST reveals objects that appear too massive, too compact, or too evolved for their inferred age, it is not contradicting direct predictions so much as exposing where extrapolation loses reliability. This has important consequences for how certainty is communicated. Observational astronomy often speaks in confidence intervals, detection thresholds, and statistical significance. But interpretation carries an additional layer of uncertainty that is harder to quantify. When a property is inferred through models rather than measured directly, uncertainty becomes structural rather than statistical. The object discussed here exemplifies this distinction. Its light is detected, its spectrum is measured, its redshift is constrained. Those data are solid. What remains uncertain is the mapping between those measurements and physical interpretation. Does brightness imply stellar mass in the same way at this epoch? Does compactness imply maturity or simply different assembly pathways? These questions cannot be resolved by better signal-to-noise alone. As a result, confidence must be recalibrated, not lowered arbitrarily, but contextualized properly. A single object can be confidently real while its implications remain provisional. This distinction is essential to avoid false dichotomies between revolution and error. Modern cosmology increasingly operates under this condition. Large surveys deliver precision, but interpretation depends on assumptions that are no longer invisible. JWST has made those assumptions explicit by pushing beyond their tested domain. This shift affects how results are framed in both academic and public discourse. Headlines often seek clarity. Something either breaks physics or confirms it. Reality is subtler. Objects like this one neither overthrow theory nor neatly conform to it. They highlight where theory is incomplete, not incorrect. In response, cosmologists are adjusting their language. Phrases like tension with models or unexpected efficiency are replacing stronger claims. This reflects a healthy recognition that uncertainty is not a weakness, but an accurate description of the current state of knowledge. The challenge lies in maintaining rigor without overstating conclusions. Overinterpretation risks creating crises where none exist. Underinterpretation risks missing genuine insights. Balancing these pressures requires patience, replication, and restraint. This balancing act is not new. It accompanied the first detections of dark energy, the early debates over galaxy formation timelines, and the discovery of quasars. In each case, initial uncertainty gradually resolved as datasets expanded and theory adapted. The difference now is speed. JWST accelerates discovery faster than consensus can form. That acceleration places new demands on methodology. Statistical samples must grow before anomalies can be contextualized. Independent pipelines must confirm measurements. Alternative explanations must be explored systematically rather than dismissed or embraced prematurely. The object's role, then, is less about its individual properties and more about what it reveals regarding process. It shows how modern cosmology must operate when observation outruns explanation. It demonstrates that confidence is no longer a simple function of data quality, but of theoretical maturity. This has downstream effects on model building. Instead of optimizing for a single best-fit universe, theorists increasingly explore ensembles of possible histories. Variability becomes a feature rather than a bug. Rare outcomes are incorporated rather than excluded. This shift aligns theory more closely with the diversity now observed. Communication also adapts. Rather than presenting the universe as largely settled with minor refinements remaining, cosmology increasingly emphasizes open questions and probabilistic outcomes. JWST's discoveries reinforce this framing by showing that early cosmic history is richer and less uniform than previously assumed. Importantly, this does not erode trust in cosmology. It strengthens it. Science gains credibility when it accurately represents uncertainty rather than concealing it. Objects like this one demonstrate that cosmology remains a living discipline, responsive to evidence rather than committed to narrative closure. As more JWST data arrive, confidence will not collapse. It will reorganize. Some tensions will dissolve as selection effects are understood. Others will persist and guide refinement. The process will be iterative, not disruptive. The next section explores how this recalibration of confidence feeds directly into model development, shaping new frameworks for early structure formation that are flexible enough to accommodate diversity without abandoning physical constraint. Chapter 20. Modeling the Unexpected: How Theory Responds to Frontier Objects. When observations move into regimes where theory is weakly constrained, model development shifts from prediction to accommodation. This does not mean theory becomes reactive or unprincipled. It means that its role changes. Instead of narrowing outcomes to a small set of expected behaviors, models must account for a wider range of physically plausible histories. The object revealed by JWST sits squarely within this transition, acting as a forcing function on how early universe modeling is conducted. Most galaxy formation models were built to reproduce average behavior. They aim to match large-scale statistics, mass functions, luminosity distributions, and clustering properties. These approaches are effective when samples are large and diversity averages out. They are less effective when rare or extreme systems are detected, particularly when those systems exist at epochs where assumptions were extrapolated rather than tested. The appearance of an object with unusual compactness, brightness, or inferred efficiency challenges how feedback, cooling, and collapse are implemented in models. In many simulations, star formation efficiency is capped by feedback processes that expel gas or heat it sufficiently to halt further collapse. These prescriptions are calibrated using later galaxies where metals, radiation fields, and turbulent structures are well developed. Applying them unchanged to earlier epochs may impose artificial limits. In response, theorists are revisiting how efficiency is treated under primordial conditions. Low metallicity gas behaves differently, cooling channels change, fragmentation thresholds shift. In some regimes, gas can collapse rapidly without forming extended stellar distributions. This does not violate physics, but it does fall outside simplified prescriptions optimized for later times. Another area of revision concerns timescales. Many models implicitly assume that star formation and structural assembly proceed gradually. JWST data suggests that under certain conditions, these processes can be compressed into shorter intervals. Rapid assembly does not require exotic physics, but it does require allowing for synchronized inflow, efficient angular momentum loss, and limited early feedback. Compactness also plays a role. Objects that assemble mass into small volumes early will appear mature even if their total mass is modest. Traditional size-mass relations may not apply cleanly at high redshift. Models that enforce these relations by construction risk misclassifying such systems as impossible rather than rare. Dark matter treatment is also under scrutiny. While the standard cold dark matter framework remains robust at large scales, its small-scale behavior depends on assumptions about halo concentration, merging history, and baryonic coupling. Extremely compact systems may form within unusually concentrated halos or experience atypical merger pathways. These scenarios are allowed but underrepresented in coarse-grained models. Importantly, theory is not scrambling to explain a single object. Instead, it is preparing for the likelihood that this object represents a class rather than an outlier. Early indications from JWST suggest that diversity at high redshift is greater than expected. Modeling efforts are therefore shifting toward exploring parameter space more broadly rather than optimizing for a narrow outcome. This shift is computationally demanding. Exploring rare configurations requires high-resolution simulations with fine-grained physics, which are expensive and time-consuming. As a result, semi-analytic models and controlled numerical experiments are being used to probe specific mechanisms rather than entire populations. There is also renewed emphasis on falsifiability. Models that accommodate everything explain nothing. The challenge is to identify which physical changes are necessary and which are optional. Does reproducing this object require altering feedback strength, changing initial conditions, or allowing for alternative assembly pathways? Each option has distinct consequences that can be tested against future observations. JWST plays a central role in this process. Its ability to measure spectra, sizes, and environments provides constraints that models must respect. As more objects are catalogued, correlations will emerge that either support or eliminate proposed mechanisms. Theory advances not by fitting one object, but by surviving comparison with many. This iterative process reflects how frontier science progresses. Observation identifies possibilities. Theory explores mechanisms. Further observation narrows the field. The object in question has advanced this cycle by exposing where models were overly restrictive rather than fundamentally flawed. Crucially, no single model revision has yet emerged as dominant. Multiple pathways remain viable. This is expected at an early stage. Theoretical convergence follows data accumulation, not individual discoveries. What has changed is emphasis. Efficiency, compactness, and rapid assembly are no longer treated as pathological. They are treated as conditional outcomes that must be explained rather than excluded. This represents a philosophical shift as much as a technical one. The broader implication is that early universe theory is entering a phase of expansion rather than refinement. The parameter space of plausible histories is growing before it contracts again. Objects like this one define the boundaries of that space. The next section examines how this modeling shift influences expectations for what JWST and future observatories are likely to find next, and how prediction adapts when uncertainty is structural rather than temporary. Chapter 21. Prediction under uncertainty. What comes after the first anomaly? Once an object forces theory into expansion rather than refinement, the nature of prediction changes. Instead of asking what should exist, researchers begin asking what could exist without violating known physics. This transition marks a critical phase in any observational era. It reflects a moment when instruments have outpaced assumptions and certainty gives way to structured uncertainty. JWST's discovery has placed early universe research squarely in this phase. Traditional prediction relies on constrained parameter spaces. Models produce expectations, how many objects of a given mass should exist, how bright they should be, how quickly they should evolve. These expectations guide observation strategies and define what counts as surprising. But when an object appears that sits near or beyond these boundaries, prediction must be recalibrated. The goal shifts from forecasting exact outcomes to mapping ranges of plausibility. In this context, prediction becomes probabilistic rather than deterministic. Instead of stating that objects like this should be rare or impossible, theorists now assign likelihoods to classes of formation pathways. Some pathways may produce compact, efficient systems early. Others may lead to diffuse, slowly evolving ones. The existence of one extreme object increases the probability that others exist nearby in parameter space, even if they differ in detail. One immediate implication is that JWST is unlikely to remain a singular case. If the physics that allowed this object to form operates under common early universe conditions, then similar systems should appear as survey coverage expands. They may not be identical in mass or luminosity, but they should share structural or spectral traits that indicate comparable histories. Prediction therefore turns toward pattern recognition. Rather than expecting replicas, astronomers look for families of objects connected by shared characteristics. These may include unusually compact sizes, elevated luminosity to mass ratios, or spectral signatures indicating intense early activity without extended stellar buildup. Each new detection refines the emerging pattern. This approach also influences where astronomers look. Instead of focusing exclusively on regions expected to host typical galaxies, surveys are adjusted to probe environments where extreme outcomes are more likely. These include dense early filaments, regions of rapid gas inflow, or halos forming near critical mass thresholds. Prediction guides targeting, but with broader criteria. Importantly, uncertainty does not imply randomness. Physical laws still constrain outcomes. Cooling rates, gravity, radiation pressure, and angular momentum conservation all impose limits. The difference is that the range of viable initial conditions is wider than previously assumed. Prediction becomes an exercise in bounding rather than pinpointing. Another consequence concerns timescales. Models now allow for rapid transitions between states that were once thought to require long evolution. Objects may pass through luminous, compact phases briefly before dispersing or transforming. Prediction must therefore account for observability windows. Some objects may exist only long enough to be detected in deep surveys, but not in shallower ones. This temporal aspect complicates expectations. The absence of similar objects in earlier datasets may reflect selection effects rather than true rarity. JWST's sensitivity and wavelength coverage allow it to catch systems during brief, extreme phases that previous instruments missed. Prediction must now incorporate observational bias explicitly. The role of falsification also evolves. Instead of testing whether a specific model is correct, researchers test whether proposed mechanisms overproduce or underproduce certain classes of objects. If future JWST observations reveal many similar systems, some explanations will become untenable due to excess predictions. If few appear, others will be constrained. Prediction becomes iterative, continuously updated by new data. This framework also prepares the field for surprises beyond the initial anomaly. Once models loosen overly strict assumptions, they may predict additional unexpected outcomes. Some of these may already be present in JWST data, but not yet recognized. Others may emerge as analysis techniques improve. Prediction thus becomes exploratory, guiding attention rather than declaring conclusions. Crucially, this does not weaken science. It strengthens it by aligning expectations with evidence. Periods of high uncertainty are not failures of theory, but signs of discovery-driven progress. Historically, similar phases followed the discovery of quasars, pulsars, and cosmic microwave background anisotropies. In each case, prediction adapted before converging again. JWST's role in this process is ongoing. Each new observation reduces uncertainty incrementally, patterns will sharpen, outliers will be contextualized, prediction will gradually regain precision, but with revised assumptions that reflect what the universe has revealed rather than what was inferred in its absence. The next stage will involve testing whether this object represents an extreme tail of known distributions or a distinct population with its own formation logic. That distinction carries profound implications. If it is a tail, models must explain why tails extend so far. If it is a population, models must explain why it was previously invisible. Either outcome reshapes how early cosmic structure is understood. Prediction under uncertainty is therefore not a pause in understanding, but a necessary bridge between surprise and explanation. The following chapter examines how this object influences interpretations of cosmic rarity itself, whether the universe is more exceptional than models suggest, or whether human expectations have simply been too narrow. Chapter 22: Rarity, Bias, and the Problem of Cosmic Expectations. When an object appears to violate expectations, the immediate question is whether the object is genuinely rare, or whether the framework used to judge rarity is incomplete. In cosmology, rarity is not an intrinsic property. It is inferred from models, surveys, and assumptions about what should be visible. JWST's detection of a highly unusual deep space object forces a reassessment of how rarity itself is defined and measured. Cosmic expectations are built on layered assumptions. The first layer concerns physics, how matter behaves under gravity, radiation, and thermodynamic constraints. The second layer concerns initial conditions, how density fluctuations were distributed in the early universe. The third layer concerns observation, which objects instruments are capable of detecting. An object that appears rare may challenge any one of these layers, or all three simultaneously. Historically, many objects now considered common were initially thought to be extraordinary. Quasars were once regarded as inexplicable anomalies. Pulsars were briefly considered possible artificial signals. In each case, rarity was overestimated because the relevant populations were poorly sampled. The lesson is not that anomalies disappear, but that rarity often reflects observational incompleteness rather than physical improbability. JWST complicates this picture by dramatically expanding the observable volume of the universe. It does not simply see farther, it sees differently. Its sensitivity to infrared wavelengths allows it to detect objects whose light has been stretched by cosmic expansion, as well as systems obscured or invisible to earlier telescopes. This shift means that populations previously absent from datasets may suddenly appear. The unusual object at the center of this discussion may therefore represent a class that was always present but observationally inaccessible. If so, its perceived rarity is a function of instrumental limitation rather than cosmic scarcity. Determining which interpretation is correct requires understanding selection bias in detail. Selection bias enters at multiple stages. Survey design determines which regions of the sky are observed and for how long. Data processing pipelines favor certain morphologies and brightness profiles. Classification algorithms are trained on known object types and may misclassify or overlook unfamiliar structures. Each step filters reality through expectation. JWST mitigates some biases while introducing others. Its deep field observations probe small areas with extraordinary sensitivity, making them ideal for detecting faint or compact objects. However, these fields represent tiny fractions of the sky. An object detected in such a field may seem rare simply because comparable surveys have not been conducted elsewhere. Assessing rarity therefore requires scaling detections appropriately. If one object is found in a small surveyed volume, statistical models can estimate how many might exist across the full sky. These estimates carry large uncertainties, but they provide context. An object that appears unique locally may correspond to a substantial unseen population globally. Another factor is temporal bias. Some objects may exist only briefly in cosmic time. If their observable phase is short, their detection probability is low, even if they form frequently. JWST's ability to capture such transient phases increases the chance of encountering systems that were previously missed. Their apparent rarity may reflect fleeting visibility rather than uncommon formation. Cosmic variance further complicates interpretation. The universe is not perfectly uniform at small scales. Certain regions may host atypical structures due to local density fluctuations or environmental effects. Detecting an extreme object in one region does not guarantee similar objects elsewhere, but it also does not imply uniqueness. The challenge is distinguishing between statistical outliers and indicators of new populations. Outliers can often be accommodated by extending existing distributions. New populations require additional formation mechanisms or revised physics. The distinction depends on whether further observations reveal continuity or separation between known objects and the anomaly. JWST's growing dataset will be decisive. If additional objects share key properties with the initial discovery, rarity will be reinterpreted as undersampling. If not, the object may remain singular, demanding explanation as an extreme outcome of known processes or as evidence of overlooked physics. Importantly, rarity alone does not imply significance. Some rare objects have little impact on broader theory. Others force fundamental revisions. Significance depends on whether the object exposes a gap between observation and prediction that cannot be closed without changing assumptions. In this case, the object's properties intersect with core questions about early structure formation, energy distribution, and the efficiency of cosmic processes. Its significance therefore extends beyond its frequency. Even if it remains rare, it constrains what the universe is capable of producing. Cosmology advances by adjusting expectations to match evidence. JWST's role is not to confirm comfort, but to test boundaries. Rarity, when properly contextualized, becomes a diagnostic tool rather than a verdict. It reveals where understanding is thin and where models must be stress-tested. The next step is examining how theorists respond to such stress tests. How models are modified, extended, or replaced when confronted with objects that resist classification. That response determines whether anomalies remain curiosities or become turning points in how the universe is understood. Chapter 23: Theory Under Pressure: How Models Respond to the Unexpected. When observations resist classification, theoretical models do not collapse immediately. Instead, they are placed under pressure. That pressure reveals which assumptions are flexible, which are foundational, and which may no longer be justified. JWST's identification of an object that defies standard categories has initiated this process across multiple areas of astrophysical theory. Most cosmological models are constructed to explain populations rather than individuals. They are calibrated against large datasets and tuned to reproduce statistical trends. When a single object appears anomalous, the first response is to test whether it can be accommodated as an extreme case within existing distributions. This involves extending parameter ranges rather than altering mechanisms. For example, formation efficiency may be increased, collapse time shortened, or environmental density raised within plausible limits. In many cases, this approach succeeds. Astrophysical systems often occupy broad continua, and rare outcomes are expected. However, tension arises when accommodating an object requires pushing multiple parameters simultaneously to their extremes. When efficiency, timing, compactness, and luminosity must all be maximized at once, the probability of such a configuration drops sharply. At that point, models begin to strain. The object observed by JWST presents this kind of compound challenge. It does not merely exceed expectations in one dimension. Its inferred mass-to-light ratio, spatial compactness, apparent age, and energy output all sit near or beyond predicted bounds. Adjusting one parameter is insufficient. Several must be revised together, increasing the likelihood that underlying assumptions are incomplete. One assumption under review is the sequencing of structure formation. Standard models assume that stars form first, enriching their surroundings and gradually assembling larger systems. Compact, luminous objects without clear stellar buildup challenge this sequence. In response, theorists explore pathways where gas collapses rapidly before fragmenting, producing dense central objects early. Another area of pressure concerns feedback processes. Stellar winds, radiation, and supernovae are assumed to regulate growth by heating and dispersing gas. If an object forms efficiently despite limited stellar activity, feedback models may overestimate suppression at early times or in certain environments. Revising feedback strength has consequences across galaxy evolution theory. Dark matter behavior also enters the discussion. Many models assume smooth, collisionless dark matter halos. However, small-scale structure remains an area of uncertainty. Variations in dark matter distribution or interaction could alter collapse dynamics, enabling compact objects to form more readily. While such ideas remain speculative, anomalies sharpen interest in their implications. Importantly, theoretical response is constrained by consistency. Any modification must still reproduce the vast body of observations that existing models explain well. This limits how radically assumptions can be changed. The challenge is finding adjustments that resolve anomalies without introducing new conflicts elsewhere. In practice, this leads to the exploration of hybrid scenarios. Instead of single mechanisms, models combine processes that operate sequentially or concurrently. Rapid gas inflow may create dense cores, followed by delayed star formation. Early accretion may produce luminosity spikes before stabilization. Such scenarios increase explanatory flexibility, but also complexity. Theoretical work also distinguishes between necessary and sufficient conditions. An anomaly may require specific conditions to form, but those conditions need not be common. This allows models to explain rarity without redefining typical outcomes. The question becomes whether the required conditions are physically plausible within known cosmic environments. JWST's data provide constraints that guide this evaluation. Spectral properties, spatial profiles, and environmental context limit which scenarios remain viable. Models that predict features inconsistent with these observations can be discarded. In this way, anomaly-driven theory refinement remains evidence-based rather than speculative. Another consequence is increased emphasis on predictive differentiation. Competing models may all explain the initial object, but differ in what else they predict. Some may imply the existence of related systems at different masses or stages. Others may predict associated phenomena, such as specific emission lines or surrounding structures. These predictions guide future observations. The process is iterative. Observation pressures theory, theory generates new expectations, and observation tests them again. JWST accelerates this cycle by providing data at unprecedented depth and resolution. Anomalies therefore propagate through theory more rapidly than in previous eras. Crucially, theory under pressure does not imply theory in crisis. It reflects healthy scientific adaptation. Many foundational models have survived similar challenges by evolving rather than being replaced. The current situation suggests expansion of framework rather than abandonment. The object's greatest theoretical impact may not be the specific explanations it demands, but the humility it enforces. It reminds researchers that models are approximations shaped by available data. As observational reach extends, approximations must be reassessed. The next question is whether this anomaly remains isolated or signals a broader mismatch between expectation and reality. That determination depends on how many similar objects JWST uncovers and how diverse they are. The implications extend beyond theory to how future missions are designed and how cosmology prioritizes unanswered questions. The following chapter examines how this discovery influences observational strategy itself, how astronomers decide where to look next when the universe reveals that it is more varied than anticipated. Chapter 23. Theory under pressure: how models respond to the unexpected. When observations fall outside established expectations, theoretical models are not discarded immediately. Instead, they are subjected to stress. This stress reveals which assumptions are flexible, which are foundational, and which may require revision. The object identified by JWST has introduced such pressure across multiple areas of astrophysical theory, not because it is poorly understood, but because it is well measured and still difficult to reconcile with existing frameworks. Most cosmological models are designed to describe populations rather than individual cases. They are calibrated using large data sets and validated by their ability to reproduce statistical distributions of galaxy properties across cosmic time. When a single object appears anomalous, the initial response is to test whether it can be accommodated as an extreme outcome within known distributions. This process involves extending parameter ranges rather than introducing new mechanisms. For example, theorists may increase assumed formation efficiency, shorten collapse timescales, or place the object in an unusually dense environment. Each adjustment is evaluated independently to determine whether it remains consistent with known physics. In many historical cases, this approach has been sufficient. Astrophysical systems often occupy wide continua, and rare outcomes are expected even in well-understood processes. The difficulty arises when multiple parameters must be adjusted simultaneously. The JWST object challenges expectations not in one dimension, but across several. Its inferred compactness, luminosity, apparent formation timing, and energy output all approach or exceed predicted bounds. Adjusting one parameter alone does not resolve the discrepancy. Accommodating the object requires coordinated shifts across multiple assumptions, which reduces statistical plausibility within existing models. This has prompted reassessment of several foundational assumptions. One concerns the sequence of structure formation. Standard models assume that stars form first, gradually enriching their surroundings and building galaxies over time. Compact, luminous objects appearing before substantial stellar populations challenge this ordering. In response, theorists explore scenarios in which gas collapses rapidly into dense configurations before fragmenting into stars. Such scenarios do not violate known physics, but they were previously considered inefficient or rare. JWST data suggest that under certain early universe conditions, these pathways may be more viable than assumed. High gas density, low metallicity, and limited angular momentum can suppress fragmentation and enable rapid central collapse. These conditions are not exotic, but their combined effect may have been underestimated. Feedback processes represent another area under pressure. Stellar winds, radiation pressure, and supernova explosions are assumed to regulate growth by heating and dispersing gas. If an object forms efficiently, despite limited stellar activity, feedback prescriptions may overestimate suppression in early or low metallicity environments. Revising feedback strength has consequences beyond a single object, affecting predictions for galaxy growth across cosmic time. Dark matter behavior also enters the discussion. Most models assume dark matter is cold, collisionless, and smoothly distributed at small scales. However, small-scale structure remains an area of uncertainty. Variations in halo concentration or early clustering could alter collapse dynamics, enabling compact systems to form more readily. While such adjustments remain conservative, anomalies increase interest in their implications. Importantly, theoretical response is constrained by consistency. Any modification must preserve agreement with the vast body of observations that existing models explain successfully. This limits how radically assumptions can be changed. Models cannot be tuned to explain one object at the expense of many others. The challenge lies in identifying adjustments that resolve anomalies while maintaining overall coherence. In practice, this leads to hybrid scenarios. Instead of relying on a single dominant mechanism, models combine processes that operate sequentially or concurrently. Rapid gas inflow may create dense cores, followed by delayed star formation. Early accretion may produce brief luminosity peaks before stabilizing. These scenarios increase explanatory flexibility while remaining grounded in known physics. Theoretical work also distinguishes between necessary and sufficient conditions. An anomaly may require specific conditions to form, but those conditions need not be common. This allows models to explain rarity without redefining typical outcomes. The question becomes whether the required conditions plausibly occur within early cosmic environments at the inferred frequency. JWST observations provide constraints that guide this evaluation. Spectral properties limit allowable temperatures and compositions. Spatial profiles restrict collapse geometries. Environmental context constrains interaction histories. Models that predict features inconsistent with these observations can be excluded, narrowing the range of viable explanations. Another consequence of theoretical pressure is emphasis on predictive differentiation. Competing models may all explain the initial object, but differ in what else they predict. Some imply the existence of similar systems at different masses or evolutionary stages. Others predict associated structures, emission signatures, or spatial clustering. These differences guide future observations and provide pathways for falsification. The process is iterative. Observation pressures theory, theory generates new expectations, and observation tests them again. JWST accelerates this cycle by delivering data with unprecedented sensitivity and resolution. As a result, anomalies propagate through theoretical frameworks more rapidly than in previous observational eras. Crucially, theory under pressure does not imply theory in crisis. It reflects a normal stage of scientific adaptation. Many foundational models have survived similar challenges by expanding rather than being replaced. The current situation suggests refinement of early universe assumptions rather than abandonment of established cosmology. The broader impact of this object may lie less in the specific explanations it demands, and more in the methodological shift it enforces. It highlights the limits of inference based on incomplete data and demonstrates how new instruments recalibrate expectations. As JWST continues to observe, theoretical models will increasingly be shaped by what is seen rather than what was presumed. The next question is how these pressures influence observational strategy itself. When theory adapts to anomalies, observation adapts in response. The following section examines how discoveries like this reshape where astronomers look, what they prioritize, and how future searches are designed in light of an expanding landscape of cosmic possibilities. Chapter 24: Redirecting the Search: How Anomalies Reshape Observation Strategy. When theory adjusts in response to unexpected observations, observation itself must also change. Instruments do not merely collect data, they embody assumptions about what is worth looking for, where it is likely to be found, and how it should appear. The detection of a deeply unusual object by JWST has begun to reshape those assumptions, prompting a reassessment of observational strategy across deep space research. Historically, survey design has been guided by models that prioritize efficiency. Telescopes are pointed toward regions expected to maximize return. Dense galaxy fields, known overdensities, or environments predicted to host luminous systems. Classification pipelines are optimized to recognize familiar morphologies and spectral signatures. This approach has been highly successful in building comprehensive catalogs of galaxies, stars, and active nuclei. However, it also embeds bias. Objects that deviate strongly from expected forms are more likely to be missed, misclassified, or discarded as noise. JWST's discovery challenges the adequacy of these assumptions. The object in question was detected not because it fit a predicted template, but because the telescope's sensitivity allowed it to register signals that would previously have been indistinguishable from background fluctuations. Its recognition required careful inspection rather than automated classification. This highlights the need for strategies that prioritize anomaly detection alongside population statistics. One immediate response has been increased attention to low-signal regimes. Observers are re-examining faint detections near survey thresholds, particularly those that were previously considered marginal. Instead of treating low signal-to-noise features as expendable, teams now evaluate whether such features display internal consistency across wavelengths or epochs. This shift increases workload, but expands discovery space. Field selection is also under review. Deep field observations traditionally balance depth against sky coverage. JWST's deepest fields probe extremely small areas, raising questions about representativeness. An anomaly detected in such a field may reflect local conditions rather than universal trends. In response, observational programs increasingly favor coordinated surveys across multiple independent fields to assess whether unusual objects recur. Temporal strategy matters as well. Some extreme objects may be visible only during brief evolutionary phases. Short-lived luminosity peaks, rapid structural transitions, or transient emission features can all escape detection if surveys are static. JWST's scheduling flexibility allows repeated observations of the same field, enabling time domain analysis even in deep space. This capability is becoming more central as theorists recognize the importance of transient visibility. Another strategic shift concerns wavelength prioritization. The object's detectability depended on JWST's infrared sensitivity, which reveals features inaccessible to optical instruments. As a result, observational plans increasingly emphasize multi-wavelength coordination. Objects identified in infrared surveys are cross-referenced with radio, submillimeter, and X-ray data to construct more complete physical profiles. This reduces reliance on any single diagnostic and mitigates classification ambiguity. Data analysis methods are evolving in parallel. Automated pipelines remain essential for handling JWST's data volume, but anomaly-aware algorithms are being developed to flag unusual combinations of properties rather than reject them. Machine learning tools trained exclusively on known object classes risk reinforcing bias. New approaches incorporate uncertainty and novelty detection, allowing systems to highlight objects that differ statistically from established populations. Human oversight remains critical in this process. Many of the most interesting JWST discoveries have emerged from careful visual inspection and cross-comparison rather than automated output alone. This reinforces the value of mixed methodologies that combine computational efficiency with expert judgment. Resource allocation is another consequence. Objects that challenge theory attract disproportionate attention, drawing telescope time for follow-up observations. This introduces tension between comprehensive surveys and targeted study. While population-level understanding remains essential, anomalies often drive theoretical progress. Observational planning increasingly seeks balance between breadth and depth. The impact extends beyond JWST itself. Future missions are influenced by what JWST reveals. Instrument designers reconsider sensitivity requirements, wavelength coverage, and survey strategies in light of newly observed phenomena. If extreme objects occupy parameter spaces previously unexplored, future telescopes may be optimized to probe those spaces more efficiently. This feedback loop between discovery and design is a hallmark of observational progress. An instrument reveals something unexpected, prompting refinement of both theory and future observation. JWST sits at the center of such a loop, accelerating it by compressing timescales between detection and interpretation. Importantly, strategic adjustment does not imply indiscriminate searching. Observational time remains limited and priorities must be set. The challenge is identifying which anomalies represent meaningful gaps in understanding and which are statistical curiosities. This assessment relies on theoretical context, reproducibility, and potential explanatory reach. The object discussed here meets several criteria that elevate its importance. It intersects with foundational questions about early structure formation, energy distribution, and the efficiency of cosmic processes. Its properties cannot be easily dismissed as measurement error or minor deviation. As a result, it has become a reference point for rethinking how deep space observation is conducted. Redirecting observational strategy is therefore not a reactionary step, but a rational response to expanded empirical reality. JWST has demonstrated that the universe contains configurations not fully anticipated by existing models. Observational strategy must adapt to ensure such configurations are not overlooked in the future. The final question is how this adaptive process influences the broader narrative of cosmology. When instruments repeatedly reveal structures that strain expectation, the story told about the universe evolves. The following chapter examines how such discoveries reshape interpretation itself, how cosmology integrates the unexpected into a coherent account without forcing premature closure. Chapter 25. An Open Universe: What the Bizarre Object Ultimately Changes. The most consequential impact of JWST's discovery is not tied to the final classification of the object itself. Its significance lies in how it alters the posture of cosmology moving forward. Rather than resolving a specific mystery, the object expands the space in which explanations must operate. It forces a reconsideration of how completeness, confidence, and closure are treated in a field where observational reach is still rapidly advancing. For much of modern cosmology, progress has followed a pattern of convergence. Observations narrowed uncertainties, models became increasingly precise, and large-scale structure appeared broadly understood. The universe seemed complex, but governed by a stable framework. JWST has not overturned that framework, but it has demonstrated that its margins are less settled than assumed. The discovery underscores that agreement at large scales does not guarantee understanding at small or extreme ones. This realization reframes the role of anomalies. Instead of being treated as problems to be eliminated, they become indicators of where models are incomplete. The bizarre object identified by JWST does not negate existing theory, but it reveals where theory operates with limited empirical grounding. In doing so, it restores a sense of openness to a discipline that had begun to emphasize refinement over exploration. The object also highlights the conditional nature of classification. Much of astrophysics depends on placing systems into categories: galaxies, stars, black holes, nebulae. These categories are useful, but they are abstractions. Objects that resist classification expose the assumptions embedded in those abstractions. They demonstrate that nature does not always respect conceptual boundaries designed for convenience. This has methodological consequences. Cosmology increasingly relies on probabilistic reasoning rather than categorical certainty. Objects are evaluated based on likelihoods, parameter ranges, and model compatibility, rather than definitive labels. JWST's discovery accelerates this shift by showing that definitive labels may be unavailable even with high-quality data. There is also an epistemological implication. The object serves as a reminder that observational access defines understanding. What was once invisible shaped theory through absence. What becomes visible reshapes it through presence. JWST's sensitivity does not merely add data points. It changes which questions can be asked meaningfully. Some debates that were previously speculative are now empirical, while others emerge newly formed. Importantly, the discovery does not imply that the universe is chaotic or unknowable. It implies that the universe is more permissive than expected. It allows configurations that were considered unlikely, inefficient, or transient. This permissiveness does not violate physical law, but it stretches intuition built on incomplete sampling. The broader narrative of cosmic evolution remains intact. Gravity still structures matter. Radiation still shapes thermodynamics. Expansion still governs large-scale behavior. What changes is the range of outcomes permitted within those constraints. The universe appears capable of producing structure under a wider variety of conditions than previously demonstrated. This has implications beyond early universe studies. Small-scale behavior influences interpretations of dark matter, feedback processes, and the emergence of complexity. Objects at the edge of detectability provide leverage on these questions, precisely because they operate where constraints are weakest. The bizarre object functions as such leverage. It also influences how certainty is communicated. Public narratives often emphasize discovery as resolution. In practice, discovery often introduces ambiguity. JWST's finding exemplifies this. It does not provide a clear answer, but it clarifies where answers are lacking. That clarification is itself progress. Future observations will determine whether this object is isolated or representative. If similar systems are found, they will form a new population requiring systematic explanation. If not, the object will remain an extreme case, demanding explanation within existing distributions. In either scenario, its impact persists. The open-ended nature of this outcome is not a failure of science. It is characteristic of moments when observation outpaces expectation. Such moments historically precede major advances, not because they immediately reveal new laws, but because they expose where understanding is incomplete. JWST's role is ongoing. As data accumulate, patterns will emerge or dissolve. Models will adjust incrementally. Some explanations will be ruled out, others refined. The bizarre object will either find its place within an expanded framework or continue to sit at its edge, defining the boundary of current knowledge. What changes permanently is the recognition that deep space still holds configurations that resist easy explanation. JWST has not closed the book on cosmic structure. It has opened a new chapter, one where certainty is provisional, categories are flexible, and discovery remains driven by what the universe reveals rather than what models predict. The object stands as evidence that the universe is still capable of surprising those who study it carefully, not through spectacle, but through quiet inconsistency. That inconsistency does not demand alarm, it demands attention. The discovery made by the James Webb Space Telescope does not represent a failure of existing cosmological theory, but it does expose the limits of how confidently those theories can be applied to the earliest and most extreme environments in the universe. The object examined throughout this script challenges expectations not because it contradicts known physics outright, but because it occupies a region of parameter space that had not been adequately tested by observation before JWST. What makes this discovery significant is not its strangeness in isolation, but the way it intersects with multiple areas of astrophysics at once. Its properties strain assumptions about formation timescales, energy efficiency, structural organization, and environmental influence. Each of these tensions is manageable individually. Taken together, they reveal that current models rely on simplifications that hold well for typical systems but weaken at the margins. JWST has demonstrated that the early universe was capable of producing configurations that were previously theoretical or underestimated in likelihood. This does not require abandoning established frameworks such as gravitational collapse, hierarchical structure formation, or dark matter-dominated growth. It requires acknowledging that these processes can operate under a wider range of conditions than previously confirmed by data. The response to this discovery illustrates how cosmology advances. Observation identifies a discrepancy. Theory adapts by revisiting assumptions, expanding viable pathways, and generating new testable predictions. Follow-up observations then determine which explanations remain consistent with reality. This iterative process is not a sign of uncertainty in science, but of its self-correcting nature. Whether this object represents a rare extreme or the first identified member of a broader population remains an open empirical question. Future JWST surveys, along with complementary observations from other instruments, will determine how common such objects are and how they fit into the larger picture of cosmic evolution. Regardless of the outcome, the discovery has already fulfilled an important role by refining the questions that matter most. The universe revealed by JWST is not fundamentally different from what theory predicted, but it is more detailed, more varied, and less constrained by prior expectations. As observational reach increases, cosmology moves from inference toward direct testing, particularly at the boundaries where theory is least certain. This discovery reinforces a central lesson of modern astronomy. Understanding the universe is not a process of confirming what is already known, but of identifying where knowledge remains incomplete. JWST has extended that boundary. What lies beyond it will be defined not by speculation, but by continued observation,